Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the vast preparations for humanity's return to lunar space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The moon pulls at Earth with the same force it has exerted for 4.5 billion years. Tonight, as engineers make final calculations and astronauts review procedures, that ancient gravitational embrace prepares to guide human beings beyond Earth's atmosphere once more. The Artemis II mission represents humanity's first crewed journey to lunar space since December 1972, when Eugene Cernan and Harrison Schmitt became the last humans to walk on another world. For 51 years, the moon has waited in its silent orbit, its surface undisturbed by footprints, its ancient secrets preserved in vacuum and radiation. The gravitational force that will carry 4 crew members away from Earth operates according to Newton's inverse square law, a mathematical relationship discovered in 1687 that governs everything from falling apples to orbiting galaxies. Each kilogram of spacecraft mass feels the moon's pull with a force that decreases precisely as the square of the distance between them. This same force lifted the first tides across Archean shores 3.5 billion years ago, when Earth rotated in 6-hour days and the moon hung 3 times closer in a salmon-colored sky, its surface still glowing with the heat of formation. In the Vehicle Assembly Building at Kennedy Space Center, the Space Launch System rocket stands 322 feet tall, containing enough liquid hydrogen to fill 33 Olympic swimming pools and enough liquid oxygen to supply a small city's breathing needs for several months. The rocket's main engines burn these propellants at temperatures exceeding 300 to 300 degrees Celsius, hot enough to melt copper, aluminum, and most of the elements that compose the human body. The Orion spacecraft perched atop this controlled explosion contains life support systems designed to function in an environment where atmospheric pressure measures 0. Background radiation increases by factors of hundreds, and a single seal failure means unconsciousness in 15 seconds and death in 2 minutes. Only took half a century to engineer humanity's return to this particular intersection of physics and mortality. The crew capsule's heat shield measures 5 meters across and weighs more than a small automobile, composed of a honeycomb structure filled with Avcoat ablative material that will sacrifice itself to protect 4 human lives during atmospheric reentry. This shield represents the accumulated knowledge of every spacecraft that has ever returned to Earth at lunar velocities, from the Soviet lunar sample return missions to the Apollo command modules that carried 24 astronauts safely home from the moon between 1968 and 1972. Each hexagonal tile of ablative material embodies lessons learned from spacecraft that became shooting stars, their crews saved by margins measured in degrees of angle and seconds of time. The launch window for Artemis II opens and closes according to orbital mechanics first described by Johannes Kepler in 1609, when he discovered that celestial bodies move in ellipses rather than the perfect circles assumed by 2 millennia of astronomical tradition. Kepler's laws now determine the precise moments when Earth's rotation, the moon's orbital position, and the spacecraft's intended trajectory align with mathematical precision. A delay of even a few minutes can shift the mission's duration by hours, alter fuel requirements by hundreds of kilograms, and change the recovery zone by thousands of kilometers. The same gravitational mathematics that govern this launch window also predict that the Moon retreats from Earth by 3.82 centimeters annually, approximately the rate at which human fingernails grow. This recession began the moment the Moon formed, likely through a collision between early Earth and a Mars-sized protoplanet that astronomers call Theia. The impact vaporized both worlds' crusts, flung molten rock into orbit, and left Earth spinning once every 5 hours beneath a ring of glowing debris that gradually coalesced into the Moon we see today. Scientists still debate whether Theia struck at a glancing angle or nearly head-on, whether the collision occurred 5 billion years ago or somewhat later, and whether the Moon formed from the impactor's material, Earth's mantle, or some mixture of both. What remains beyond dispute is that without this ancient catastrophe, Earth's rotational axis would wobble chaotically over periods of millions of years. Seasons would shift unpredictably between tropical and Arctic extremes, and complex life might never have found the stable climate necessary for multicellular evolution. The same Moon that may have enabled human consciousness now calls that consciousness back across 400,000 kilometers of vacuum. The 4 crew members chosen for this mission, Christina Hammock-Koch, Victor Glover, Jeremy Hansen, and Reed Wiseman, will experience gravitational forces their bodies have never encountered. During launch, they will weigh nearly 4 times their normal weight as the rocket accelerates to escape velocity. In the weightlessness of space, their bones will begin losing calcium within hours. Their cardiovascular systems will decondition as blood redistributes throughout their bodies, and their spatial orientation will depend entirely on visual references through spacecraft windows. Upon return, atmospheric entry will subject them to forces 8 times greater than their Earth weight, enough to make their arms feel like concrete pillars and their heads weigh as much as bowling balls. Only took evolution 4 billion years to produce organisms capable of surviving such elegant violence. The mission's free return trajectory follows a figure-8 path around the Moon that requires no engine burns to bring the crew home safely. This gravitational lifeline was first calculated for Apollo 8 in 1968, when 3 astronauts became the first humans to leave Earth's gravitational sphere of influence and see the planet as a complete sphere hanging in space. The mathematics of free return trajectories represent a partnership between human engineering and celestial mechanics, an acknowledgement that in the vast emptiness between worlds, gravity itself becomes both the greatest danger and the most reliable ally. As final preparations continue, the Moon completes another orbit in its ancient dance around Earth, moving through space at 1.23 meters per second along an elliptical path that brings it as close as 356,500 kilometers and carries it as far as 406,700 kilometers from Earth's center. The Moon's gravitational influence reaches far beyond these distances, creating bulges in Earth's oceans that follow its position across the sky, generating tidal currents that have shaped coastlines since water first collected in permanent basins 3.5 billion years ago. The crew will join a select group of humans who have experienced what Apollo 8's Frank Borman described as the most beautiful, warm, and lonely thing he had ever seen Earth as viewed from lunar distance, suspended in the cosmic dark like a blue marble veined with white clouds and brown continents. This perspective, known as the overview effect, has transformed the worldview of nearly every astronaut who has experienced it, replacing national and ideological boundaries with an understanding of Earth as a single, fragile ecosystem surrounded by hostile emptiness. The Artemis II mission carries forward humanity's longest sustained technological project, the step-by-step expansion of human presence beyond Earth's protective atmosphere and magnetic field. Each system aboard the spacecraft represents solutions to problems that have no terrestrial equivalent: how to provide breathable air without an atmosphere, how to maintain comfortable temperatures in an environment that alternates between the searing heat of direct sunlight and the absolute cold of shadow. How to navigate without magnetic compasses in a realm where up and down become arbitrary designations. Tonight, as Earth rotates beneath stars that have watched the moon's retreat for billions of years, 4 human beings prepare to experience the profound transition from planet-bound to space-traveling life. The same gravitational forces that assembled the solar system from cosmic dust will guide them across the void, carrying them toward discoveries that cannot yet be imagined and returning them to the world that shaped their consciousness across 4 billion years of evolutionary time. The moon waits in patient orbit, its ancient surface scarred by 4.5 billion years of cosmic impacts, its gravitational embrace unchanged since the first tides washed over lifeless shores. Soon, human eyes will again witness the curvature of space-time made visible, as Earth's horizon bends away into the star-filled darkness that surrounds all worlds. The Orion spacecraft rests atop its tower like a seed balanced on the tip of a controlled explosion, its heat shield facing downward toward the launch pad that has witnessed humanity's most ambitious departures. Within the crew module, switches and displays await human touch for the first time since the final Orion test flight circled Earth unmanned in 2022. The capsule's interior measures 25 meters in height and 5 meters in diameter dimensions that will contain 4 human lives for the next 10 days as they journey farther from home than any people have traveled since the Nixon administration. The spacecraft's life support systems maintain an artificial atmosphere at sea-level pressure, filtering carbon dioxide through lithium hydroxide canisters and generating oxygen through water electrolysis, the same chemical process that occurs in Earth's ancient oceans when lightning splits water molecules into hydrogen and oxygen. Each breath the crew takes will be recycled air, purified by machines that must function flawlessly in an environment where the nearest repair shop lies 400,000 kilometers away. The redundancy built into these systems reflects a sobering truth in space. There are no emergencies, only catastrophes that happen slowly enough to allow problem solving, and catastrophes that happen too quickly for solutions. Only took 60 years of spaceflight to make mechanical breathing seem routine. The moment of ignition arrives with the precision that orbital mechanics demands. The Space Launch System's 4 RS-25 engines ignite first, their hydrogen-oxygen combustion producing exhaust temperatures of 3,300 degrees Celsius and steam clouds that billow across the Florida wetlands like artificial weather. These engines burned on 37 space shuttle missions, each one tested and refurbished after every flight, their turbopumps spinning at 37,000 revolutions per minute, fast enough to empty an average swimming pool in 25 seconds. The 2 solid rocket boosters ignite 6.6 seconds later, adding 3.6 million pounds of thrust that lifts 2.6 million kilograms of rocket, fuel, and human ambition away from Earth's surface. The acoustic energy released during launch measures 180 decibels at the launch pad, loud enough to kill unprotected humans through sound alone and powerful enough to be heard clearly from 25 kilometers away. Sound waves travel through the humid Florida air at 343 meters per second, reaching nearby wildlife refuges as a rolling thunder that sends birds into flight and alligators sliding into protective waters. The same physics that governs this acoustic violence also determines how sound travels through the vacuum of space, which is to say, not at all. Within minutes of launch, the crew will enter a realm of absolute silence, broken only by the sounds they bring with them, the hum of life support systems, the whisper of air circulation, and their own voices speaking across the void. As the rocket climbs, Earth's gravitational field weakens according to Newton's inverse square law, but the effect remains imperceptible until the spacecraft reaches orbital velocity. At an altitude of 100 kilometers, the arbitrary boundary between atmosphere and space, the crew experiences their first taste of weightlessness as the main engines shut down and momentum carries them forward at 7.8 kilometers per second. This velocity represents humanity's minimum speed for leaving the planet fast enough to fall around Earth's curvature rather than toward its surface, slow enough to remain gravitationally bound to the world that launched them. The transition from weight to weightlessness occurs in seconds, as the crew's inner ears lose their gravitational reference point and their cardiovascular systems begin adapting to the absence of hydrostatic pressure gradients. Pencils float away from writing surfaces. Water forms perfect spheres instead of drops. And the human vestibular system, evolved over millions of years to function in Earth's gravitational field, begins the confused process of adaptation that astronauts politely call space sickness. The crew's bodies will spend the next several days learning to function in an environment that no terrestrial evolution has prepared them for. Scientists still debate whether prolonged weightlessness represents a fundamental barrier to human expansion beyond Earth, or merely another adaptation challenge similar to those overcome by the first amphibians that left the ocean 365 million years ago. What remains certain is that every minute spent in microgravity brings measurable changes. Bone density decreases by 1 to 2% per month. Muscle mass atrophies despite rigorous exercise, and the cardiovascular system deconditions as the heart no longer needs to pump blood against gravity's downward pull. Only took evolution 4 billion years to perfect systems that become liabilities within hours of leaving the planet. The spacecraft's trajectory follows a carefully calculated path that will carry it beyond Earth's gravitational sphere of influence, the Hill sphere, named for the American mathematician George William Hill, who in 1878 first calculated the region where one celestial body's gravity dominates over another's. For Earth, this sphere extends approximately 1.5 million kilometers toward the Sun, encompassing the Moon's orbit and defining the boundary beyond which solar gravity begins to dominate over terrestrial attraction. The Artemis II crew will spend most of their mission within this sphere, gravitationally bound to Earth even as they travel farther from home than any humans since 1972. The rocket's upper stage burns liquid hydrogen and liquid oxygen in a combustion reaction that produces only water vapor and temperatures hot enough to melt tungsten. This clean-burning propulsion represents one of the purest forms of energy release available to human engineering, the same fusion of hydrogen and oxygen that powers the Sun, scaled down to dimensions that can lift 4 human beings beyond Earth's atmosphere. The exhaust velocity of these engines reaches 4 kilometers per second, approaching the theoretical maximum efficiency possible with chemical propulsion. As the spacecraft climbs away from Earth, the crew experiences their first view of the planet's curvature, a gentle arc that becomes more pronounced with each passing minute. At 400 kilometers altitude, Earth's horizon displays the thin blue line of atmosphere that contains all the air every human has ever breathed. A layer so thin that if Earth were shrunk to the size of an apple, the atmosphere would be thinner than the apple's skin. Beyond this fragile boundary lies the cosmic radiation environment that has bathed the solar system for billions of years, filtered only by planetary magnetic fields and the tenuous solar wind. The spacecraft's guidance systems navigate using a combination of GPS signals, star trackers, and inertial measurement units that can detect accelerations as small as 1/1,000,000th of Earth's gravity. These instruments maintain position accuracy within meters across distances of hundreds of thousands of kilometers, using the same mathematical principles that allowed Polynesian navigators to find remote Pacific islands by reading wave patterns and stellar positions. The difference lies only in the precision, where ancient navigators accepted margins of error measured in kilometers. Space navigation demands accuracy measured in centimeters. Temperature regulation becomes a constant challenge as the spacecraft alternates between sunlight and shadow, experiencing temperature swings from 120 degrees Celsius in direct solar radiation to minus 160 degrees Celsius in Earth's shadow. The crew module's thermal protection system uses multi-layer insulation and active heating systems to maintain a shirt sleeve environment inside a capsule that could otherwise freeze or roast its occupants within minutes. This thermal management represents one of spaceflight's most elegant solutions, creating a tiny pocket of terrestrial environment that travels through conditions hostile to all known forms of life. The ascent continues according to schedules written in orbital mechanics and propellant margins, carrying 4 human beings away from the only world known to harbor life. Below them, Earth rotates at 465 meters per second at the equator, its 24-hour day marking time in a universe where days and nights are arbitrary human constructs imposed on the ceaseless motion of planets around stars. The spacecraft climbs toward an appointment with emptiness, following trajectories calculated to intersect with a world that has been falling around Earth for 4.5 billion years. Beyond Earth's protective atmosphere, the spacecraft enters a realm where charged particles stream through emptiness like invisible rain. The Van Allen radiation belts encircle Earth in 2 distinct zones, named for James Van Allen, who discovered them in 1958 through data transmitted by the first American satellite, Explorer. 1. These belts trap high-energy protons and electrons within Earth's magnetic field, creating regions where radiation levels rise to hundreds of times the doses that would trigger immediate evacuation of nuclear power plants on Earth's surface. The inner belt extends from approximately 1,000 to 6,000 kilometers above Earth's surface, populated primarily by protons with energies exceeding 100 million electron volts, particles moving at significant fractions of light speed, accelerated by the planet's magnetic field into stable orbits that can persist for years or decades. The outer belt stretches from 13,000 to 60,000 kilometers altitude, dominated by electrons that spiral along magnetic field lines in patterns that fluctuate with solar activity and geomagnetic storms. Between these belts lies a region of relatively low radiation called the slot region, where particle densities drop by factors of hundreds, a quiet zone in Earth's magnetic architecture that spacecraft often use as a refuge during extended missions. The 4 crew members aboard Artemis II will traverse both radiation belts during their outbound journey, their bodies exposed to cosmic ray doses accumulated over months of terrestrial living, compressed into minutes of passage through magnetically trapped particles. The spacecraft's aluminum hull provides minimal shielding against high-energy protons, which penetrate metal with the ease of light passing through window glass. Each crew member wears a personal dosimeter that clicks softly as radiation passes through their bodies, Geiger counter, percussion, marking time in a realm where time itself becomes measured in particle impacts per second rather than heartbeats per minute. Only took the universe 13 billion years to create magnetic fields capable of trapping the very particles that enable stellar fusion. Scientists still debate the full biological effects of acute radiation exposure during rapid transit through the Van Allen belts, but decades of research on atomic bomb survivors, nuclear accident victims, and previous astronauts provide sobering reference points. High-energy particles damage DNA through direct ionization and the creation of free radicals, reactive molecules that can alter genetic information with surgical precision. The human body's repair mechanisms can address most radiation damage given sufficient time, but the concentrated exposure during belt passage challenges cellular repair systems evolved under the gentle radiation environment of Earth's surface. The spacecraft's passage through the inner belt occurs at 11 kilometers per second, reducing exposure time to approximately 15 minutes a brief but intense encounter with particles that have been imprisoned in Earth's magnetic field since the planet's magnetosphere first formed over 3 billion years ago. These trapped particles represent a fossil record of ancient solar activity, high-energy remnants of solar storms that occurred when Earth's surface still glowed with the heat of formation and the Moon hung 3 times closer than it does today. The outer Van Allen belt presents different challenges, its electron population varying dramatically with solar cycle phase and geomagnetic activity during solar maximum. Coronal mass ejections can pump additional particles into the outer belt, increasing radiation levels by factors of 10 or more within hours. Conversely, during solar minimum, the outer belt can nearly empty as particles precipitate into Earth's upper atmosphere, creating aurora displays that paint the polar skies in green and red light. The Artemis II mission launches during solar cycle 25, when moderate solar activity provides predictable but elevated radiation levels throughout the belt system. The crew's radiation exposure accumulates according to principles first described by Marie Curie, whose work with radium in the early 1900s established the fundamental relationship between radioactive decay and biological damage. Each particle impact transfers energy to cellular structures through electromagnetic interactions governed by quantum mechanics, the same physics that allows electrons to orbit atomic nuclei and enables chemical bonds to form between atoms. The microscopic violence of radiation damage occurs at scales billions of times smaller than the spacecraft itself. Individual particles disrupting individual molecules within individual cells of 4 human beings traveling through the emptiness between worlds. Magnetic field lines threading through the Van Allen belts follow paths described by Maxwell's equations, discovered in the 1860s when earthbound physicists first began to understand the relationship between electricity and magnetism. These same equations govern the behavior of Earth's magnetosphere, the solar wind that streams past Earth at 400 kilometers per second, and the electromagnetic fields that trap charged particles in stable orbits around the planet. The spacecraft follows a trajectory that cuts across magnetic field lines like a needle threading through invisible fabric, each intersection marking another step in humanity's journey away from terrestrial protection. Temperature control becomes increasingly challenging as the spacecraft moves beyond Earth's shadow, where direct solar radiation heats exposed surfaces to temperatures that would melt lead while shadowed areas plunge toward absolute zero. The crew module's thermal management system maintains internal temperatures within the narrow range required for human survival, using radiators that glow cherry red as they dump waste heat into the vacuum of space. This thermal balancing act represents one of the most elegant aspects of spacecraft design, creating a stable environment for biological life within a vehicle traveling through conditions that would instantly kill any known organism. The passage through the radiation belts occurs in relative silence, marked only by the soft clicking of dosimeters and the steady hum of life support systems that maintain Earth-normal atmospheric pressure and composition within the crew module. Outside the spacecraft windows, Earth continues to shrink, its blue marble appearance becoming more pronounced as distance reduces continental details to brown and green patches separated by white cloud formations that spiral in patterns driven by the Coriolis effect, the same rotational force that will later influence the spacecraft's trajectory as it approaches the Moon. Scientific instruments throughout the spacecraft record radiation levels, magnetic field strength, and particle velocities that will contribute to humanity's understanding of the space environment beyond Earth's protective atmosphere. Each measurement adds to a database that began with Explorer 1's discovery of the Van Allen belts and continues through every mission that ventures beyond low Earth orbit. This accumulated knowledge represents one of space exploration's most practical achievements, the systematic mapping of hazards that future astronauts will encounter during journeys to Mars, the asteroid belt, and eventually the outer planets, where radiation levels increase by orders of magnitude. The spacecraft's computers process thousands of measurements per second, monitoring radiation exposure, spacecraft health, and trajectory accuracy with digital precision that would have seemed miraculous to the engineers who launched Apollo missions using slide rules and mechanical calculators. Modern spaceflight represents a partnership between human intuition and computational power, astronaut experience and automated systems, analog understanding and digital precision. The crew trusts their lives to machines that think faster than human consciousness, but lack the adaptability that evolution refined across billions of years. As the spacecraft climbs beyond the outer Van Allen belt, radiation levels drop to the background cosmic ray flux that permeates interplanetary space, a gentle drizzle of high-energy particles that has bathed the solar system since stars first began fusing hydrogen into helium. The crew has successfully navigated Earth's magnetic prison, emerging into the cosmic radiation environment that will accompany them throughout their journey to the Moon and back. Behind them, Earth's magnetosphere continues its ancient work of deflecting solar wind and trapping charged particles, creating the radiation belts that have challenged every human venture beyond low orbit since the space age began. Earth retreats in the spacecraft's windows like a blue marble rolling away across black velvet, its familiar continents becoming abstract patches of brown and green, separated by the swirling white spirals of weather systems that have churned through the atmosphere for billions of years. At a distance of 100,000 kilometers, the planet measures approximately 1 degree across roughly the apparent size of a basketball held at arm's length. The crew experiences what Apollo 8's William Anders described as the most profound perspective shift in human history, watching their entire world shrink to a point of light suspended in cosmic darkness. The pale blue dot phenomenon, named by Carl Sagan after Voyager 1's famous photograph of Earth from beyond Neptune's orbit, transforms the crew's understanding of scale and significance with mathematical precision. Each kilometer of distance reduces Earth's apparent diameter by a calculable fraction. Following the inverse relationship between distance and angular size that governs all astronomical observations. The same geometric principles that allow astronomers to measure stellar distances through parallax now demonstrate to 4 human beings that their home world occupies an infinitesimally small volume of space in a universe composed primarily of emptiness. Only took 4.5 billion years of evolution to produce organisms capable of seeing their birth world from the outside. The spacecraft's trajectory carries it along a path first calculated by celestial mechanicians in the 1960s, when human computers, primarily women mathematicians working at NASA, used mechanical calculators and logarithmic tables to solve the 3-body problem that governs motion in Earth-Moon space. The gravitational interaction between Earth, Moon, and spacecraft creates a dynamic system described by differential equations that have no closed-form analytical solution, requiring numerical integration methods that break complex motions into thousands of small computational steps. Each calculation builds upon Isaac Newton's law of universal gravitation, published in 1687, which revealed that the same force governing falling apples also guides planetary motion and spacecraft trajectories across interplanetary distances. The crew's isolation becomes more profound with each passing hour, as radio signals take increasingly longer to travel between the spacecraft and mission control in Houston. At Earth's surface, electromagnetic radiation travels at light speed 299,792 458 meters per second through an atmosphere that barely affects radio wave propagation. In the vacuum of space, these same radio waves maintain their speed but must cross ever greater distances, introducing delays that transform real-time conversation into a more patient form of communication. When the spacecraft reaches lunar distance, radio signals require 1.3 seconds to travel each direction, creating a 2/6-second delay that makes spontaneous dialogue impossible. The psychological effects of increasing isolation have been studied since the first long-duration space missions in the 1970s, when Soviet cosmonauts spent months aboard Salyut space stations and reported symptoms ranging from mild depression to acute homesickness. The Earth-shrinking phenomenon intensifies these effects as the planet transitions from a vast landscape visible through spacecraft windows to a distant point of light that could be covered by an extended thumb. The crew maintains psychological connection to Earth through scheduled communication sessions, shared meals eaten while watching Earth rotate through day and night cycles, and the knowledge that their trajectory will inevitably return them to the world that shaped their consciousness across millions of years of human evolution. Scientists still debate whether the overview effect, the profound shift in awareness reported by astronauts who see Earth from space, represents a genuine expansion of human consciousness, or merely the psychological result of experiencing an unprecedented perspective. What remains undisputed is that every astronaut who has traveled beyond low Earth orbit returns with a transformed understanding of planetary boundaries, national divisions, and humanity's place in the cosmic order. The crew of Artemis II joins a select group of 24 humans who have experienced this perspective shift, carrying forward an understanding that transcends terrestrial politics and cultural divisions. The spacecraft's life support systems maintain an artificial environment that recreates Earth's atmospheric conditions with mechanical precision. Oxygen concentrations remain constant at 21% through electrolysis of recycled water. Carbon dioxide levels stay below toxic thresholds through chemical scrubbing systems, and atmospheric pressure matches sea level conditions despite the perfect vacuum that surrounds the crew module. These systems represent humanity's most sophisticated attempt to carry terrestrial life into an environment where every parameter required for biological survival, temperature, pressure, atmospheric composition, radiation shielding, must be artificially maintained through technological intervention. The crew's daily routine follows schedules designed to maintain circadian rhythms despite the absence of natural day-night cycles. Every 90 minutes, the spacecraft passes through Earth's shadow, experiencing sunrise and sunset at 16 times the normal rate as it orbits the planet before beginning its trans-lunar injection burn. Artificial lighting within the crew module mimics terrestrial daylight cycles, while melatonin supplements help regulate sleep patterns disrupted by the constantly changing light conditions outside the spacecraft windows. These interventions acknowledge that human physiology evolved under Earth's 24-hour rotation cycle and struggles to adapt to the arbitrary day-night patterns experienced during spaceflight. Temperature regulation becomes a constant challenge as the spacecraft alternates between direct solar heating and the radiative cooling of shadow passage. External surfaces experience temperature swings of nearly 300 degrees Celsius, while internal systems must maintain the narrow temperature range required for electronic equipment and human survival. The thermal management system uses a combination of passive radiators, active heaters, and multi-layer insulation to create stable thermal conditions within a vehicle exposed to temperature extremes that would instantly kill unprotected humans. Only took technology 4 decades to make extreme temperature survival seem routine. The Earth's magnetic field weakens with the cube of distance, following mathematical relationships that govern all electromagnetic phenomena in space. At lunar distance, the planet's magnetosphere provides virtually no protection against cosmic radiation, solar wind, or the high-energy particles that stream through interplanetary space at significant fractions of light speed. The crew relies entirely on the spacecraft's passive shielding aluminum hull thickness measured in millimeters to protect them from radiation levels that would prove fatal during extended exposure. Navigational accuracy becomes increasingly critical as distance from Earth reduces the precision of ground-based tracking systems. The spacecraft's inertial guidance system uses gyroscopes and accelerometers to maintain orientation and velocity information independent of external references, while star trackers photograph constellations and compare their positions to onboard star catalogs updated with proper motion data extending thousands of years into the past and future. These navigation systems represent the culmination of techniques developed by Polynesian wayfinders who crossed thousands of kilometers of open ocean using stellar positions, refined through centuries of maritime navigation, and perfected during the space age when precision requirements increased from kilometers to meters to centimeters. The crew's perspective on time begins to shift as they move beyond Earth's gravitational dominance and experience the relativistic effects described by Einstein's theories of special and general relativity. Although these effects remain negligible at spacecraft velocities far below light speed, atomic clocks aboard the spacecraft tick at slightly different rates than identical clocks on Earth's surface, demonstrating the fundamental relationship between gravity, velocity, and the passage of time itself. The same physics that governs GPS satellite timing corrections now influences the crew's experience of duration and simultaneity as they travel farther from the gravitational field that shaped human understanding of temporal flow. Communication with Earth becomes increasingly precious as distance transforms casual conversation into carefully planned exchanges separated by growing delays. The crew's voices travel across emptiness at the speed of light, carrying human thoughts and emotions through a medium that conducts no sound, supports no life, and maintains temperatures approaching absolute zero. Each transmitted word represents a bridge between the spacecraft's artificial environment and the world that launched it, an electromagnetic connection spanning distances that dwarf all terrestrial travel. Behind the crew, Earth continues its rotation at 465 meters per second at the equator, completing another day in its 4.5 billion-year journey around the Sun. The planet's weather systems churn through patterns driven by solar heating, Coriolis effects, and the complex feedback loops that have regulated Earth's climate since atmospheric oxygen first began accumulating 3 billion years ago. From the crew's perspective, these vast atmospheric circulation patterns appear as white swirls against blue oceans and brown continents, a view of Earth's climate system that reveals its beauty and fragility with equal clarity. The spacecraft follows a trajectory governed by gravitational mathematics unchanged since Newton published the Principia in 1687, when the concept of universal gravitation first revealed that celestial and terrestrial motion obey identical physical laws. Each second of flight traces a path through space-time described by differential equations that have no simple analytical solution, requiring computers to calculate the spacecraft's position through numerical integration methods that break continuous motion into millions of discrete computational steps. The same mathematical principles that predict planetary orbits across millions of years now guide 4 human beings along a precision pathway toward the Moon's gravitational embrace. Orbital mechanics operates according to Kepler's 3 laws of planetary motion, discovered between 1609 and 1619 through careful analysis of Tycho Brahe's astronomical observations. The spacecraft's elliptical trajectory demonstrates Kepler's first law that all orbits follow conic sections, while its changing velocity throughout the journey illustrates his second law, which states that objects sweep out equal areas in equal time intervals. The mission's 10-day duration reflects Kepler's third law, relating orbital period to the semi-major axis of the trajectory through a mathematical relationship that applies equally to planets, asteroids, spacecraft, and artificial satellites. Only took humanity 3 centuries to transform abstract mathematical relationships into practical navigation tools for interplanetary travel. The translunar injection burn begins precisely on schedule, as the spacecraft's service module engine ignites for the burn that will carry the crew beyond Earth's gravitational sphere of influence. The engine produces 33,000 newtons of thrust by combining monomethyl hydrazine fuel with nitrogen tetroxide oxidizer in a hypergolic reaction that ignites spontaneously upon contact, eliminating the need for ignition systems that might fail during critical maneuvers. This chemical reaction releases energy stored in molecular bonds formed billions of years ago through stellar nucleosynthesis, when fusion processes in ancient stars created the nitrogen, carbon, and hydrogen atoms that now power humanity's return to lunar space. The engine burn lasts exactly 180 seconds, 18 minutes of acceleration that increases the spacecraft's velocity by 150 meters per second and transforms its Earth orbit into a trajectory that will carry it 400,000 kilometers away from the world that launched it. This velocity change represents one of the most significant achievements in human transportation, accelerating 4 people to speeds that exceed the escape velocity of most asteroids and approach the orbital velocities of planets in the outer solar system. The crew experiences acceleration forces of approximately 0.3 g during the burn, gentle enough to allow normal conversation, while powerful enough to alter their trajectory through space-time permanently. Mission planners calculated this trajectory using computational methods that would have required centuries of hand calculation using the mathematical tools available to Newton and his contemporaries. Modern computers solve the restricted three-body problem, the gravitational interaction between Earth, Moon, and spacecraft, by integrating the equations of motion across millions of time steps, accounting for perturbations caused by solar gravity, Earth's non-spherical shape, and relativistic corrections required for precise navigation. Each calculation represents a triumph of human mathematics over the apparent chaos of celestial mechanics, revealing the deep order underlying planetary motion. The spacecraft's guidance system updates its position estimate thousands of times per second, comparing actual trajectory with the planned flight path and calculating small correction burns needed to maintain precision navigation. These course corrections require burns measured in centimeters per second, velocity changes so small they would be imperceptible to human senses, but critical for reaching the Moon's sphere of influence at precisely the correct time and angle. The same attention to precision that allows Swiss watchmakers to create timepieces accurate to seconds per year now guides spacecraft navigation accurate to meters across interplanetary distances. Scientists still debate whether the three-body problem admits any general analytical solution, or whether numerical integration represents the only practical approach to calculating trajectories in systems dominated by multiple gravitational sources. What remains certain is that the mathematical techniques developed for spacecraft navigation have revolutionized understanding of chaotic dynamics, non-linear systems, and the fundamental predictability limits that govern complex physical processes, from weather patterns to galaxy formation. The crew's bodies continue adapting to weightlessness as their cardiovascular systems remodel themselves for an environment where blood circulation requires no work against gravitational acceleration. Bone density decreases at measurable rates as osteoclast and osteoblast cells respond to the absence of mechanical loading that has shaped vertebrate skeletal architecture for hundreds of millions of years. Muscle mass atrophies despite rigorous exercise programs designed to maintain fitness during the mission duration and prepare the crew for the physical demands of atmospheric reentry and ocean recovery operations. Only took evolution 4 billion years to perfect biological systems that become maladaptive within days of leaving the gravitational environment that created them. The spacecraft's trajectory carries it through the L1 Lagrange point, one of 5 locations where gravitational forces from Earth and Moon balanced to create regions of relative stability in the rotating Earth-Moon system. These mathematical curiosities, first described by Joseph-Louis Lagrange in 1772, represent solutions to the three-body problem where small objects can maintain fixed positions relative to two larger gravitational sources. The L1 point lies approximately 326,000 kilometers from Earth along the Earth-Moon line, marking the location where Earth's gravity exactly balances lunar gravitational attraction. Passage through the L1 point occurs without fanfare, as the crew crosses an invisible mathematical boundary marked only by subtle changes in their trajectory and the gradual transition from Earth's gravitational dominance to the Moon's sphere of influence. The spacecraft's velocity relative to Earth decreases steadily as terrestrial gravity continues pulling against their outward motion, while lunar gravity begins exerting an increasingly significant accelerating effect that will eventually capture the spacecraft into a temporary orbit around humanity's nearest celestial neighbor. Navigation accuracy becomes critical as the spacecraft approaches the boundary between Earth's Hill sphere and lunar gravitational influence, where small errors in position or velocity can result in mission-ending trajectory deviations. Ground-based tracking stations monitor the spacecraft's position using radio ranging techniques accurate to centimeters, while the crew's navigation computers maintain independent position estimates using star tracker data and inertial measurement readings. This redundancy acknowledges that in the space between worlds, navigational errors compound exponentially and rescue operations remain impossible using current technology. The crew maintains contact with Earth through radio communications that now require 1.2 seconds each direction as electromagnetic signals cross distances approaching lunar orbital radius. Mission control conversations become increasingly deliberate as real-time dialogue becomes impossible, replaced by carefully planned communication sessions where questions and responses are separated by delays that make spontaneous interaction impossible. The crew's isolation deepens with each passing hour as Earth's radio signals weaken according to the inverse square law, and the home planet shrinks to a bright star indistinguishable from Venus or Jupiter in the spacecraft's windows. Temperature management becomes more challenging as the spacecraft moves beyond Earth's shadow and experiences continuous solar heating on surfaces facing the Sun, while radiating heat to the cosmic background temperature of 2.7 Kelvin on shadowed areas. The thermal control system maintains crew comfort through a delicate balance of solar heating, electrical power consumption, and radiative cooling that must account for the spacecraft's changing orientation and distance from both Earth and Sun throughout the trajectory. The mathematical elegance of orbital mechanics reveals itself through the spacecraft's motion, as gravitational forces discovered by Newton guide four human beings along a path calculated using techniques developed by Lagrange, Euler, and other 18th century mathematicians who could never have imagined their abstract mathematical work enabling interplanetary travel. The crew follows a trajectory that represents one of humanity's most sophisticated achievements in applied mathematics, transforming centuries of theoretical investigation into practical navigation across the solar system. Ahead of the spacecraft, the Moon grows larger against the star field, its gravitational influence becoming increasingly dominant as the inverse square law amplifies lunar attraction and diminishes terrestrial gravity. The same celestial body that has influenced Earth's tides for billions of years now prepares to capture four human visitors in a gravitational embrace that will guide them around the lunar far side before returning them safely to the world that shaped their species across millions of years of evolution. The free return trajectory represents one of orbital mechanics' most elegant safety mechanisms, a gravitational lifeline that requires no fuel consumption to bring the crew home safely, even if every spacecraft system fails during the lunar portion of their journey. This figure-8 path around the Moon was first calculated for Apollo 8 in 1968, when 3 astronauts became the first humans to leave Earth's gravitational sphere of influence and experience the profound isolation of interplanetary space. The mathematics underlying free return trajectories exploit the 3-body dynamics of the Earth-Moon system, using lunar gravity itself as a natural engine that accelerates the spacecraft back toward Earth without requiring propellant reserves. The trajectory's geometry follows principles first described by Swiss mathematician Leonhard Euler in 1760, when he identified mathematical solutions to the restricted 3-body problem that governed motion in gravitational systems dominated by 2 massive bodies. Euler's work revealed that certain orbital paths naturally return to their starting points after completing figure-8 loops around gravitating masses, creating closed trajectories that repeat indefinitely unless perturbed by external forces. The Artemis II spacecraft follows one such Eulerian path, modified by 20th-century orbital mechanics to account for Earth's oblate shape, lunar orbital eccentricity, and the gravitational influences of Sun and planets. Only took mathematics 2.5 centuries to transform abstract theoretical solutions into practical life-saving trajectories for human space travelers. The spacecraft approaches the Moon's sphere of influence, the Hill sphere, extending approximately 66,000 kilometers from the lunar surface, where lunar gravity dominates over terrestrial gravitational attraction. This invisible boundary represents a mathematical construct rather than a physical barrier, defined by the distance at which the Moon's gravitational acceleration exceeds Earth's pull by a factor determined by the inverse square law and the mass ratio between the 2 bodies. Crossing this threshold marks the crew's transition from Earth satellites to temporary lunar orbiters, even though their trajectory will carry them around the Moon rather than into a stable orbit. The Moon's gravitational field strength measures 1.62 meters per second squared at the surface, approximately 1/6 of Earth's gravitational acceleration, reflecting the lunar mass of 7.35 yak, 1022 kilograms, compared to Earth's 597 x 1024 kilograms. This reduced gravity creates orbital velocities proportionally lower than those required for Earth orbit, where low Earth orbit requires speeds exceeding 7.8 kilometers per second. Lunar orbital velocity measures only 6 kilometers per second at comparable altitudes. The crew will experience this reduced gravitational environment as their trajectory curves around the Moon's far side, following a path that brings them within 100 kilometers of ancient impact craters and volcanic maria. Scientists still debate the exact mechanism of lunar formation, though most evidence supports the giant impact hypothesis proposed in the 1970s by William Hartmann and Donald Davis. According to this model, a Mars-sized protoplanet called Theia collided with early Earth approximately 4.5 billion years ago, vaporizing both bodies' silicate mantles and ejecting material into orbit that subsequently coalesced into the Moon. Alternative theories include capture of a pre-existing body, co-accretion from the same dust disk that formed Earth, or fission of lunar material from a rapidly rotating early Earth, but isotopic analysis of Apollo samples consistently supports the giant impact scenario. The crew's trajectory carries them toward gravitational forces that have shaped Earth's evolution for billions of years through tidal interactions that continue to influence both bodies. Lunar gravity raises oceanic tides up to 15 meters in height in locations like the Bay of Fundy, where coastal geometry amplifies tidal ranges to extreme values. These same tidal forces gradually slow Earth's rotation by approximately 2.3 milliseconds per century, while simultaneously accelerating the Moon in its orbit, causing it to spiral outward at 3.8 centimeters per year, the same rate at which human fingernails grow. The spacecraft's approach, velocity builds steadily as lunar gravity accelerates the crew toward their closest approach point, following energy conservation principles that have governed celestial mechanics since planetary formation began 4.6 billion years ago. The same gravitational potential energy that lifted ancient tidal bores across Precambrian shorelines now draws 4 human beings toward the airless world that has accompanied Earth throughout the entire history of complex life. Kinetic energy increases as potential energy decreases, demonstrating the mathematical relationships that Gottfried Leibniz first described as vis viva, the living force that powers all motion in the universe. Navigational precision becomes critical as the spacecraft approaches its closest lunar approach, where small errors in position or velocity can result in trajectory deviations that prevent successful return to Earth. Ground-based tracking systems maintain constant monitoring through the Deep Space Network, a global array of radio telescopes that can communicate with spacecraft throughout the solar system, despite the inverse square law that weakens radio signals across interplanetary distances. The same electromagnetic radiation that enables this communication travels at precisely the speed of light through vacuum, requiring 1. 3 seconds to cross the Earth-Moon distance and creating communication delays that transform real-time conversation into patient exchanges separated by the fundamental limitations of physics. Only took electromagnetic theory 1 century to evolve from Maxwell's equations into interplanetary communication systems spanning hundreds of thousands of kilometers. The crew prepares for their passage around the Moon's far side, where radio contact with Earth will be temporarily severed, as 3,076 kilometers of solid rock block electromagnetic communication for approximately 34 minutes. This radio silence represents one of spaceflight's most profound isolation experiences, cutting the crew's connection to the 8 billion people who share their home planet while they experience views that only 24 humans in history have witnessed. The lunar far side shows a heavily cratered surface that never faces Earth due to tidal locking, a gravitational phenomenon that synchronizes the Moon's rotation period with its orbital period around Earth. Temperature control systems work constantly to manage thermal loads as the spacecraft's orientation changes during lunar approach, with surfaces alternately facing the Sun's 1361 watts per square meter of solar radiation and the cosmic background temperature of 2.7 Kelvin that permeates intergalactic space. The crew module maintains shirt-sleeve environmental conditions through active thermal management systems that pump heat from electronics and human metabolism to radiators that glow red-hot as they dump waste energy into the vacuum surrounding the spacecraft. The trajectory's mathematical beauty becomes apparent as gravitational forces guide the spacecraft along a path that requires no fuel consumption for the primary navigation around the Moon and return to Earth. This represents one of space exploration's most efficient achievements, using the natural dynamics of the Earth-Moon system to accomplish complex trajectory changes that would otherwise require enormous propellant reserves and larger spacecraft. The free return trajectory demonstrates humanity's growing ability to work with natural forces rather than against them, exploiting the mathematical relationships that govern celestial mechanics to achieve goals that seemed impossible during earlier eras of human civilization. Ahead of the spacecraft, the Moon continues its ancient dance around Earth, completing another orbit in its 27-3-day sidereal period while maintaining the same face toward Earth that has watched terrestrial evolution unfold across billions of years. The lunar surface awaits 4 human visitors who will add their names to the select list of people who have traveled beyond Earth's gravitational protection and experienced the profound perspective shift that comes with seeing their home planet as a distant blue star suspended in cosmic darkness. The spacecraft approaches the boundary where radio signals can no longer penetrate the Moon's bulk, preparing to enter the most profound isolation experienced by humans since Apollo 17 departed lunar orbit in December 1972. Radio silence begins as 3,576 kilometers of solid rock, compressed regolith, impact breccia, and ancient basaltic flows block electromagnetic communication with Earth for the first time in the crew's lives. The moon's far side awaits them with a landscape unmarked by atmospheric weathering, unprotected by magnetic fields, and unchanged since the late heavy bombardment sculpted its surface 4 billion years ago. The transition into radio shadow occurs gradually as the spacecraft's trajectory curves behind the lunar limb. The last radio signals from Earth fading into static that marks humanity's most complete disconnection from their home world. Mission control in Houston falls silent, 384,400 kilometers away, their voices unable to cross the vacuum between worlds when solid matter intervenes. The crew experiences the weight of absolute isolation. 4 human beings alone with their thoughts and each other while traveling at 1.6 kilometers per second around a world that has never known wind, weather, or the sound of human voices. Only took the universe 4.5 billion years to create circumstances where consciousness could experience such perfect solitude. The lunar far side reveals itself through spacecraft windows as a landscape shaped exclusively by cosmic violence. Unlike Earth's face of the moon, with its smooth maria formed by ancient lava flows, the far side displays wall-to-wall cratering that preserves a detailed record of every major impact event since the solar system's formation. The South Pole Aitken Basin stretches across 2,500 kilometers of lunar surface, one of the largest impact structures in the solar system, created when an asteroid the size of a small state struck the moon with enough energy to excavate material from the lunar mantle and scatter debris across half the moon's surface. Each crater tells a story written in physics and preserved in vacuum. The circular rims demonstrate the explosive nature of hypervelocity impacts, where kinetic energy converts to heat and shock waves with sufficient violence to melt solid rock into temporary lakes of molten basalt. Crater chains mark the paths of fragmented comets that broke apart before impact, their individual pieces striking lunar regolith in sequential explosions that created strings of circular scars across the ancient surface. Ray patterns extending hundreds of kilometers from young craters like Tycho and Copernicus record the ballistic trajectories of impact ejecta, bright streaks of pulverized rock that still contrast sharply with the darker, radiation-weathered regolith surrounding them. The absence of atmospheric protection has allowed cosmic radiation to alter the lunar surface for billions of years through a process called space weathering, where solar wind particles and micrometeorite impacts gradually darken exposed materials and create the characteristic gray regolith that covers most of the moon's surface. This same radiation environment now bathes the spacecraft and its crew, exposing them to cosmic ray fluxes that would prove fatal during extended exposure, but remain tolerable for the brief duration of their lunar flyby. Scientists still debate the exact sequence of events during the late heavy bombardment, a period approximately 4.1 to 3.8 billion years ago, when impact rates throughout the inner solar system increased dramatically before declining to current levels. Some researchers propose that gravitational resonances among the outer planets destabilized asteroid and comet orbits, sending a shower of debris toward Earth and Moon. Others suggest that the bombardment represents the final stages of planetary accretion rather than a discrete event. With impact rates declining steadily since solar system formation without requiring external triggers, the spacecraft's trajectory carries the crew over terrain that has never experienced the geological processes that constantly reshape Earth's surface. No plate tectonics recycle ancient rocks into new formations, No atmospheric weathering erodes mountain ranges into sedimentary deposits, and no water transports materials from highlands to lowlands through river systems that carve valleys and build deltas. The lunar landscape preserves 4.5 billion years of history in pristine condition, each impact crater a museum exhibit from the solar system's violent youth. Only took geological processes 4 billion years to make Earth's surface almost completely unrecognizable, while the Moon remained essentially unchanged. The crew observes the transition from lunar day to night as their trajectory carries them across the terminator, the moving boundary between sunlit and shadowed terrain that advances across the lunar surface at approximately 15 kilometers per hour during the Moon's 29.5-day synodic period. Temperatures drop precipitously in lunar shadow, from 127 degrees Celsius in direct sunlight to minus 173 degrees Celsius in areas permanently shielded from solar radiation. These extreme temperature variations reflect the absence of atmospheric heat transport that moderates terrestrial climate, creating thermal environments more severe than those found anywhere on Earth's surface. Navigation systems continue tracking the spacecraft's position using star trackers and inertial measurement units, maintaining trajectory accuracy despite the loss of ground-based radio ranging data during far-side passage. The same stellar positions that guided Polynesian navigators across thousands of kilometers of open ocean now provide reference points for 4 human beings traveling around the Moon, demonstrating the universality of celestial navigation principles across all scales of exploration from oceanic to interplanetary. The Moon's lack of atmosphere creates viewing conditions impossible anywhere on Earth, where scattered sunlight and atmospheric turbulence limit astronomical observations even from the world's highest mountains. The spacecraft's windows provide crystal clear views of star fields undimmed by atmospheric interference, revealing stellar magnitudes and colors with the clarity that ground-based astronomers can achieve only through complex adaptive optics systems designed to compensate for atmospheric distortions. Gravitational acceleration varies slightly across the lunar surface due to mass concentrations called mascons, dense regions where ancient impact events compressed lunar crustal material, or where subsurface volcanic activity created localized density anomalies. These gravitational variations influence the spacecraft's trajectory in subtle but measurable ways, requiring continuous navigation updates to maintain the precise flight path needed for successful return to Earth. The same mass concentrations that affect spacecraft orbits also influence the Moon's gravitational field as measured from Earth, creating tiny variations in lunar orbital motion that allow scientists to map subsurface density distributions using decades of laser ranging data. The crew's isolation deepens as they pass over the lunar far side's most remote regions, traveling farther from any other human beings than anyone has journeyed since the Apollo era ended half a century ago. Their radio silence represents not merely a communication blackout, but a fundamental disconnection from the electromagnetic civilization that binds Earth's 8 billion inhabitants through constant streams of digital communication. The spacecraft becomes a tiny island of human consciousness moving through an environment utterly hostile to biological life, protected from instant death only by a few millimeters of aluminum hull and the technological systems that maintain breathable atmosphere within the crew compartment. Temperature regulation becomes more challenging as the spacecraft's thermal environment changes during lunar passage, with different surfaces experiencing solar heating and radiative cooling as the vehicle's orientation shifts during its gravitational slingshot around the Moon. The crew module's environmental control systems work continuously to maintain the narrow temperature range required for human survival, while managing heat loads from electronics and crew metabolism in an environment where thermal management requires active engineering rather than passive atmospheric convection. Behind the crew, Earth remains invisible beyond the lunar horizon, its radio signals blocked by thousands of kilometers of solid rock that formed during the solar system's violent birth, when planetary embryos collided with energy sufficient to melt entire worlds. The crew continues their solitary journey around humanity's oldest celestial companion, following a trajectory that will soon carry them back into radio contact with the world that launched them on this brief exploration of the cosmos beyond Earth's protective atmosphere. The lunar surface passes beneath the spacecraft at 1.6 kilometers per second, revealing a topographical record that spans the entire history of the solar system. Ancient impact basins stretch across hundreds of kilometers, their circular outlines still visible despite billions of years of subsequent bombardment that has softened their rims and filled their floors with debris. The Mer Orientale. The ocean of storms displays its multi-ring structure with startling clarity, demonstrating the physics of hypervelocity. Impacts where asteroid-sized projectiles struck with enough energy to excavate cavities deeper than Earth's deepest ocean trenches and create shock waves that propagated through solid rock like ripples in a cosmic pond. Each crater preserves a moment frozen in geological time, when kinetic energy converted instantaneously to thermal energy and created temporary lakes of molten basalt that cooled into the smooth plains now visible as dark patches against the Moon's heavily cratered highlands. The largest impact structures, Orientale, Imbrium. Serenitatis required impactors measuring tens to hundreds of kilometers in diameter. Asteroids large enough to qualify as minor planets in their own right, before their catastrophic encounters with the early Moon transformed them into the circular features that dominate lunar topography. Only took the solar system 4.5 billion years to create a natural laboratory where every major impact event since planetary formation remains perfectly preserved in vacuum. The spacecraft's trajectory carries the crew over terrain that has experienced no geological activity since the last major volcanic eruptions ended approximately 3 billion years ago, when the Moon's interior finally cooled sufficiently to prevent further lava flows from reaching the surface. This geological death represents a natural consequence of the Moon's small size relative to Earth's insufficient mass to maintain internal temperatures high enough for sustained tectonic activity. Where Earth continues to recycle its surface through plate tectonics, seafloor spreading, and volcanic eruptions that constantly erase evidence of ancient impacts, the Moon preserves its early history with museum-like fidelity. The Mare Tranquillitatis, Sea of Tranquility, passes below the spacecraft as a dark expanse of ancient lava flows that cooled into basaltic plains, when complex life on Earth consisted of single-celled organisms floating in Archean oceans. These lunar maria formed when massive impact events fractured the lunar crust deeply enough to allow molten rock from the interior to reach the surface, flooding impact basins with basaltic lavas that solidified into the relatively smooth plains that contrast sharply with the heavily cratered lunar highlands. The same mare that provided the landing site for Apollo 11 in 1969 now serves as a navigation landmark for 4 astronauts following a trajectory that requires no propellant consumption to carry them safely around the Moon and back to Earth. Scientists have identified over 40 distinct basaltic compositions among lunar mare samples, indicating that the Moon's interior once contained a diversity of magma sources comparable to those found in terrestrial volcanic systems. Radiometric dating of Apollo samples reveals that most mare volcanism occurred between 4.2 and 3.2 billion years ago, with isolated volcanic activity continuing until approximately 1 billion years ago, far more recent than previously thought based on crater counting estimates of surface ages. This extended volcanic history suggests that the Moon's interior remained partially molten much longer than thermal evolution models predicted, possibly due to radioactive heating or tidal flexing that continue to generate internal heat sources. The crew observes the transition between mare and highland terrain, where ancient impact events excavated material from depths of tens of kilometers and distributed it across vast areas as breccia deposits and impact melt sheets. Highland rocks represent the Moon's primitive crust, composed primarily of anorthosite, a rock type rich in plagioclase feldspar that crystallized from a global magma ocean during the first few 100 million years after lunar formation. This primordial crust preserves chemical signatures of the giant impact that created the Earth-Moon system, providing scientific evidence for one of the most violent events in terrestrial planet formation. Only took geological processes billions of years to create surface compositions that tell the story of planetary formation with chemical precision. The absence of atmospheric weathering has preserved impact glass beads, cosmic ray tracks, and solar wind implantation signatures that would be quickly destroyed on Earth through interaction with water, oxygen, and biological processes. Each grain of lunar regolith represents a micrometeorite impact site, where hypervelocity collisions with particles ranging from dust specks to boulder-sized fragments have gradually pulverized solid bedrock into the characteristic powder that covers most lunar surfaces. This space weathering process continues today at rates that darken exposed materials and create the mature regolith that gave the Moon its characteristic gray appearance when viewed from Earth. Impact crater morphology reveals the physics of hypervelocity collisions through features that scale predictably with impact to size and velocity. Simple bowl-shaped craters result from relatively small impacts, while complex craters display central peaks, terraced walls, and extensive ejecta deposits that demonstrate the transition from excavation-dominated to modification-dominated impact processes. The largest basins show multiple ring structures that formed when shock waves propagated through solid rock and created concentric zones of fracturing extending hundreds of kilometers from the impact site. The spacecraft's passage over the lunar far side provides views of the most heavily cratered terrain in the solar system, where impact crater densities reach saturation levels that prevent accurate counting of individual features. This cratering saturation represents the accumulated bombardment history of the inner solar system, preserved on a world that lacks the geological processes that have erased most impact evidence from Earth, Venus, and Mars. Each crater contributes to a statistical record that allows scientists to estimate impact rates throughout solar system history and understand the evolution of the asteroid and comet populations that continue to threaten all planetary bodies. Navigation systems track the spacecraft's position relative to prominent lunar landmarks, using the same principles that allowed Apollo crews to navigate visually using distinctive crater patterns and mountain ranges. The largest lunar impact basins serve as navigation references visible from hundreds of kilometers away. Their circular outlines and characteristic lighting patterns providing positional information accurate enough for orbital navigation even without electronic guidance systems. This visual navigation capability represents an essential backup system for missions venturing beyond Earth orbit, where GPS satellites cannot provide positioning data and crews must rely on celestial navigation techniques refined over centuries of maritime exploration. Temperature measurements across the lunar surface reveal thermal environments more extreme than those found anywhere on Earth, ranging from 127 degrees Celsius in direct sunlight to minus 233 degrees Celsius in permanently shadowed polar regions where water ice may have accumulated over billions of years. These thermal extremes result from the Moon's 5-day rotation period, which exposes each point on the surface to continuous sunlight for approximately 2 weeks, followed by 2 weeks of darkness unmoderated by atmospheric heat transport. The crew's trajectory carries them over terrain that will soon host human settlements if current Artemis program plans succeed, transforming the moon from a destination visited briefly by 24 Apollo astronauts into humanity's first permanent extraterrestrial colony. The same gravitational forces that guide their spacecraft around the lunar far side will eventually capture cargo landers, crew vehicles, and the infrastructure needed to establish a sustained human presence on a world that has waited 4.5 billion years for visitors capable of appreciating both its scientific significance and its profound beauty. Radio contact with Earth remains severed as the spacecraft continues around the lunar far side, maintaining the crew's complete isolation while they experience views that fewer humans have witnessed than have traveled to the deepest ocean trenches or climbed the world's highest mountains. Their solitary passage around humanity's nearest celestial neighbor continues according to gravitational laws that have governed celestial mechanics since stars first began forming from the cosmic dust and gas that filled the early universe. The mare imbrium spreads beneath the spacecraft like a frozen sea of ancient lava, its dark basaltic surface recording volcanic eruptions that occurred when Earth's continents consisted of scattered microcontinents separated by vast Archean oceans, teeming with stromatolites and cyanobacteria. This sea of rains formed approximately 9 billion years ago when a 150-kilometer asteroid struck the moon with enough energy to excavate a cavity 300 kilometers across and trigger volcanic eruptions that continued for hundreds of millions of years. The impact shock waves fractured lunar crust to depths exceeding 60 kilometers, creating pathways for molten basalt to reach the surface and flood the impact basin with successive lava flows that cooled into the smooth plains now visible as Earth's most prominent lunar feature. The spacecraft's trajectory carries the crew over terrain where robotic explorers have searched for evidence of recent volcanic activity. Discovering lunar pyroclastic deposits that indicate explosive volcanism continued much later than previously thought. These volcanic glass beads, scattered across thousands of square kilometers, formed when gas-rich magmas erupted explosively rather than effusively, creating fire fountains that distributed molten droplets across the lunar surface like cosmic rain. The same volcanic processes that create Hawaiian fire fountains once operated on the moon, though in the absence of atmospheric pressure that would have contained and modified the eruption dynamics, only took planetary science half a century to discover that the moon's geological history extends far beyond the simple impact-dominated narrative suggested by early telescopic observations. The basaltic composition of Mare lavas reveals the moon's interior chemistry through samples that Apollo astronauts collected from 6 landing sites between 1969 and 1972. These rocks contain titanium concentrations reaching 13% by weight, in some locations far higher than typical terrestrial basalts, and indicating that lunar magma sources included exotic minerals like ilmenite that rarely contribute to volcanic eruptions on Earth. The high titanium content creates distinctive spectral signatures visible from Earth-based telescopes, allowing scientists to map mare compositions across the entire lunar surface through remote sensing techniques that distinguish between different volcanic episodes and magma sources. Mare volcanism required internal temperatures high enough to melt silicate rocks at depths of several hundred kilometers, maintaining magma generation for over 1 billion years after most thermal evolution models predict the lunar interior should have solidified completely. This extended volcanic activity suggests that radioactive decay of uranium, thorium, and potassium continued heating the lunar mantle long after accretional energy dissipated, or that tidal flexing by Earth's gravity provided additional energy sources that sustained partial melting in the deep lunar interior. Scientists still debate whether the moon possesses a metallic core similar to Earth's iron-nickel core, or whether the giant impact that formed the moon preferentially removed metallic components while leaving behind a silicate-rich body with minimal core material. Seismic data from Apollo-era instruments suggest a small core measuring 200 to 400 kilometers in radius, much smaller relative to the moon's size than Earth's 3,500-kilometer core. This size difference may explain why the moon lacks a significant magnetic field today, though paleomagnetic studies of lunar samples indicate that ancient magnetic fields once existed and recorded themselves in cooling volcanic rocks. The crew observes the boundary between Maria and Lunar Highlands, where impact events excavated ancient crustal material and revealed the moon's layered internal structure through geological cross-sections preserved as crater walls and central peaks. Highland rocks represent the moon's primitive anorthositic crust, formed when plagioclase feldspar crystals floated to the surface of a global magma ocean that existed during the first few 100 million years after lunar formation. This flotation process created a low-density crustal shell that now comprises the bright highland terrain visible from Earth as the moon's lighter-colored regions. Only took igneous processes several hundred million years to differentiate the moon's interior and create the compositional layering that still influences lunar geology today. The spacecraft passes over Copernicus crater, one of the moon's youngest large-impact structures at approximately 800 million years old, formed when complex life on Earth was transitioning from single-celled to multicellular organisms during the Proterozoic Eon. The crater's well-preserved morphology demonstrates the physics of complex crater formation, where the initial excavation cavity collapsed under gravitational forces to create the terraced walls and central peak complex visible today. Copernicus represents a transitional crater size where simple bowl-shaped morphology gives way to the complex features that characterize larger impact structures throughout the solar system. The crater's extensive ray system remains visible as bright streaks extending hundreds of kilometers radially from the impact site, composed of pulverized bedrock ejected at velocities exceeding lunar escape velocity before falling back to the surface along ballistic trajectories. These rays preserve the original brightness of freshly excavated lunar material, contrasting sharply with the space-weathered regolith that has darkened over billions of years of exposure to cosmic radiation and micrometeorite bombardment. Similar ray systems surround other young craters like Tycho and Kepler, providing natural experiments in crater degradation and regolith evolution. Temperature variations across the crater floor reveal thermal properties that reflect both composition and regolith thickness, with rocky areas heating more rapidly during lunar day, while fine-grained materials maintain more stable temperatures due to their lower thermal conductivity. These thermal measurements allow scientists to map subsurface properties remotely, distinguishing between bedrock exposures and regolith-covered terrain through infrared observations that reveal how different materials respond to the extreme temperature cycling that occurs during the moon's 29.5-day rotation period. The absence of atmospheric scattering creates lighting conditions impossible anywhere on Earth, where Rayleigh scattering of sunlight creates the blue skies and gradual twilight transitions that characterize terrestrial illumination. Lunar lighting exhibits stark contrasts between brilliantly illuminated surfaces and absolute shadow regions that receive no scattered light from surrounding terrain. This harsh illumination regime challenges both human vision and photographic equipment designed for Earth's atmospheric conditions, requiring specialized techniques to capture the full dynamic range of lunar surface features. Navigation systems continue tracking the spacecraft's position using landmark navigation techniques that compare observed crater positions with detailed lunar maps compiled through decades of telescopic observation and robotic reconnaissance missions. The largest impact basins provide navigation references visible from hundreds of kilometers away, While smaller craters serve as intermediate landmarks for precise position determination, this visual navigation capability represents an essential backup for electronic systems, acknowledging that crews venturing beyond Earth orbit must maintain the ability to navigate using techniques that require no ground support or satellite assistance. The crew's passage over mare terrain provides direct observation of volcanic landforms that formed through processes similar to those creating terrestrial flood basalts. Though operating under different environmental conditions due to the Moon's reduced gravity and lack of atmospheric pressure, lunar lava flows exhibit distinctive morphologies that reflect lower viscosities and higher eruption temperatures than typical terrestrial basalts, creating features like sinuous rills that meander across mare surfaces like fossilized rivers of molten rock that cooled billions of years ago. Mare volcanism represents the Moon's most recent major geological activity, ending approximately 1 billion years ago when decreasing internal temperatures could no longer sustain the partial melting required for basalt generation. This volcanic cessation marks the Moon's transition to geological inactivity, though minor processes like impact cratering and space weathering continue to modify surface features at rates measurable only over millions of years. The crew observes a world locked in geological time, where ancient volcanic plains preserve their original morphology with clarity impossible on tectonically active planets like Earth. The spacecraft continues its gravitational slingshot around the Moon, following orbital mechanics that will soon return radio contact with Earth and restore the crew's electromagnetic connection to the world that launched them on this brief exploration of humanity's nearest celestial neighbor. Below them, mare basalts record the Moon's fiery past, while highland anorthosites preserve evidence of planetary formation processes that created the Earth-Moon system through cosmic violence that transformed the inner solar system 4.5 billion years ago. The spacecraft encounters gravitational anomalies as it passes over regions where dense concentrations of mass mascons create localized variations in the Moon's gravitational field strength. These mass concentrations, discovered during early lunar orbital missions when spacecraft trajectories deviated unexpectedly from calculated paths, represent subsurface density variations that formed when ancient impact events compressed crustal material or when volcanic activity created localized concentrations of dense basaltic rock. The Imbrium mascon alone contains enough excess mass to alter spacecraft orbits by several hundred meters over multiple orbital periods, demonstrating that the Moon's interior remains heterogeneous despite 4.5 billion years of gravitational settling. Mascon-induced trajectory perturbations occur according to Newton's law of universal gravitation, where gravitational acceleration increases locally above regions of enhanced density and decreases over areas where crustal excavation has removed material. These variations, measuring only a few milligauss, thousandths of Earth's surface gravity, prove sufficient to destabilize long-term lunar orbits and require constant orbital adjustments for spacecraft intended to maintain stable trajectories around the Moon. The Apollo command modules experience these same gravitational perturbations during their lunar orbital phases, though mission durations remain too brief for mascon effects to significantly impact crew safety or mission success. Only took celestial mechanics 3 centuries to reveal that gravitational fields possess fine structure complexity that challenges assumptions about uniform planetary mass distributions. The crew observes terrain where future Artemis missions will establish humanity's first permanent lunar base, transforming the Moon from a destination visited briefly by Apollo crews into a staging area for missions to Mars and the outer solar system. Site selection criteria include proximity to permanently shadowed polar regions, where water ice may have accumulated over billions of years, access to elevated terrain that maintains nearly continuous solar exposure for power generation, and geological stability that can support the infrastructure needed for sustained human presence beyond Earth's protective atmosphere. Lunar water ice, if present in sufficient quantities, represents one of the most valuable resources for future space exploration because it can be split electrolytically into hydrogen and oxygen, the most efficient chemical propellants available for rocket engines. This indigenous resource extraction capability, known as in situ resource utilization, could eliminate the need to transport water and propellants from Earth's deep gravitational well, reducing mission costs by factors of 10 or more and enabling the large-scale space exploration that current launch economics make prohibitively expensive. Scientists estimate that permanently shadowed regions near the lunar poles may contain billions of tons of water ice deposited by comet impacts over geological timescales. Though direct confirmation requires surface sampling missions currently planned for the late 2020s, the same impact processes that created the Moon's heavily cratered surface also delivered volatile compounds that would have been lost immediately in equatorial regions, but could survive indefinitely in polar cold traps, where temperatures remain below -200 degrees Celsius throughout the lunar day-night cycle. The spacecraft's trajectory carries the crew over potential landing sites for Artemis III, the mission that will return humans to the lunar surface for the first time since Eugene Cernan and Harrison Schmitt departed the Taurus-Littrow Valley in December 1972. Site selection considers scientific objectives, operational constraints, and safety margins that reflect 50 years of technological advancement since the Apollo era ended. Modern lunar landers will possess capabilities that Apollo-era technology could not achieve: precision landing accuracy measured in meters rather than kilometers, extended surface duration measured in weeks rather than days, and mobility ranges that extend far beyond the walking distances that limited Apollo's surface exploration. Only took human civilization 50 years to develop the technology needed to transform lunar exploration from brief visits into permanent settlement. The crew's passage over the lunar far side continues through terrain that experiences temperature extremes more severe than those found anywhere in the solar system except on planets lacking atmospheres entirely. Surface temperatures reach 127 degrees Celsius during the 2-week lunar day, hot enough to melt lead and zinc, while nighttime temperatures plunge to -173 degrees Celsius, colder than the surface of Pluto during its most distant orbital phases. These thermal extremes reflect the Moon's slow rotation period and lack of atmospheric heat transport, creating environments that challenge both robotic systems and human exploration equipment. The Mascon gravitational anomalies that perturb spacecraft trajectories also provide insights into lunar crustal structure and composition through their correlation with surface features visible from orbit. Large impact basins consistently exhibit positive gravitational anomalies, indicating that dense material, probably basaltic lava flows and impact melt sheets, fills the excavated cavities and creates mass concentrations detectable from orbital altitude. This gravitational mapping technique allows scientists to study subsurface geology remotely, revealing structural details that would otherwise require extensive drilling and sampling programs. Navigation systems compensate for Mascon perturbations through continuous trajectory monitoring and frequent course corrections that maintain the spacecraft's intended flight path despite gravitational variations. The same mathematical techniques used to model planetary motion around the Sun now account for local gravitational variations within the Moon's influence, demonstrating the scalability of celestial mechanics from solar system to planetary to local gravitational environments. Each correction burn consumes minimal propellant, but requires precise timing and execution to prevent cumulative errors that could jeopardize the mission's safe return to Earth. The crew observes impact crater morphologies that reveal the relationship between impactor properties and crater characteristics, through features that scale predictably with impact energy and target material properties. Simple craters exhibit bowl-shaped profiles with depth-to-diameter ratios near zero. While complex craters display central peaks, terraced walls, and extensive ejecta deposits that form when gravitational forces modify the initial excavation cavity. The transition between simple and complex crater morphologies occurs at approximately 15 to 20 kilometers diameter on the Moon, compared to only 2 to 4 kilometers on Earth, reflecting the influence of gravitational acceleration on crater collapse processes. The Mascon phenomenon demonstrates that planetary interiors retain heterogeneity over geological timescales, preserving density variations that record ancient impact events, volcanic episodes, and differentiation processes that occurred during the first billion years after planetary formation. These gravitational signatures provide a form of planetary archaeology, revealing subsurface structures that remain hidden from optical observations but manifest themselves through their gravitational effects on orbiting spacecraft. Only took gravitational theory 4 centuries to evolve from Newton's universal gravitation into precision techniques for mapping planetary internal structure remotely. Thermal infrared measurements reveal how different lunar surface materials respond to temperature cycling during the 29.5-day lunar rotation period, with rocky surfaces heating and cooling more rapidly than regolith-covered terrain due to differences in thermal conductivity and heat capacity. These thermal properties allow scientists to distinguish between bedrock exposures and debris-covered slopes, providing information about surface composition and regolith thickness that complements visible wavelength observations and gravitational field mapping. The spacecraft continues its precisely calculated trajectory around the Moon's far side, following orbital mechanics that exploit the three-body dynamics of the Earth-Moon system to achieve complex trajectory changes without propellant consumption. This gravitational assist technique represents one of space exploration's most elegant achievements, using natural celestial mechanics to accomplish mission objectives that would otherwise require enormous fuel reserves and correspondingly larger launch vehicles. The crew's isolation in radio shadow continues as they observe terrain that has remained essentially unchanged since the late heavy bombardment ended approximately 3.8 billion years ago, when impact rates throughout the inner solar system declined to their current levels and allowed complex geology to begin operating on Earth while the Moon entered its current era of geological quiescence. Below them, Mascons continue their ancient influence on local gravitational fields, creating the subsurface density variations that will challenge lunar orbital missions for as long as humans explore the solar system. The spacecraft emerges from behind the lunar limb like consciousness returning after deep sleep, its radio antennas automatically acquiring Earth's electromagnetic signature as 384 to 400 kilometers of vacuum once again permit communication at the speed of light. The crew experiences the relief of reconnection as their isolation ends, and voices from mission control reach across interplanetary space with the clarity that only electromagnetic radiation can provide. Radio waves penetrate the void between worlds, carrying human speech, telemetry data, and navigation updates that restore the crew's link to the 8 billion people who share their home planet, but have never experienced the profound perspective shift that comes from seeing Earth as a distant blue star. The re-establishment of radio contact occurs precisely when orbital mechanics predict, as the spacecraft's trajectory carries it beyond the Moon's radio shadow and into direct line-of-sight communication with Earth-based antennas. Signal strength increases according to the inverse square law as the spacecraft moves farther from the Moon's bulk, though transmission delays continue to lengthen as distance from Earth grows throughout the return journey. Each radio pulse travels at 299.792 458 meters per second through vacuum, requiring 1.28 seconds to cross the Earth-Moon distance and creating conversation delays that transform real-time dialogue into patient exchanges separated by the fundamental limitations of electromagnetic propagation. Only took electromagnetic theory 1 century to evolve from Faraday's experiments into communication systems spanning hundreds of thousands of kilometers of space. Mission control's voices carry updates on spacecraft systems, trajectory corrections, and weather conditions at the recovery zone in the Pacific Ocean, where the crew will complete their journey in approximately 6 days. The same radio frequencies that enable this communication also carry television signals, cellular phone conversations, and internet data streams that connect Earth's human population through electromagnetic networks invisible to human senses but essential to modern civilization. The crew's radio link represents an extension of this terrestrial communication web across interplanetary distances, demonstrating technology's ability to maintain human connection even when physical proximity becomes impossible. The spacecraft's emergence from radio shadow marks the beginning of its gravitational acceleration back toward Earth as lunar gravity completes the slingshot maneuver that will return the crew safely to their home planet. The Moon's 35,122 kilograms of mass continue influencing the spacecraft's trajectory according to Newton's inverse square law. Though this gravitational effect weakens rapidly as distance increases and Earth's much larger gravitational field begins to dominate the spacecraft's motion through space. The transition between lunar and terrestrial gravitational influence occurs gradually across thousands of kilometers, with no distinct boundary marking where one world's gravity ends and another's begins. The crew reports their observations to scientists on Earth, describing crater morphologies, mare compositions, and Maskin effects that add to humanity's accumulated knowledge of lunar geology and geophysics. These verbal descriptions complement the hundreds of photographs and thousands of instrumental measurements that the spacecraft's automated systems record throughout the lunar flyby, creating a comprehensive dataset that will guide future mission planning and scientific investigations. The same observational techniques that allowed Galileo to discover lunar mountains and craters through his primitive telescope now operate with precision that reveals subsurface density variations and thermal properties invisible to human vision. Scientists still debate whether the crew's direct observations provide scientific value beyond that obtained through robotic instruments, or whether human presence primarily serves psychological and political purposes rather than advancing lunar science. What remains certain is that human observers possess pattern recognition capabilities and adaptive intelligence that complement automated systems, particularly when unexpected phenomena require real-time decision-making or when subtle visual cues indicate scientific features that programmed instruments might overlook. Only took evolution 4 billion years to create biological intelligence capable of interpreting geological processes operating across similar timescales. The spacecraft's trajectory follows the return portion of its free return path, using the Moon's gravity to accelerate toward Earth while consuming no propellant for the primary navigation maneuver. This gravitational assist demonstrates orbital mechanics at its most elegant, exploiting the natural dynamics of celestial bodies to achieve complex trajectory changes that would otherwise require enormous fuel reserves. The mathematics underlying this maneuver trace back to 18th century work by Euler, Lagrange, and other pioneers of celestial mechanics who developed the theoretical framework that makes modern interplanetary navigation possible. Radio communications with Earth become increasingly precious as the crew shares their experiences with family members, colleagues, and the global audience following their mission through live television coverage and internet streaming. These personal conversations carry human emotions across interplanetary space at light speed, connecting 4 individuals who have experienced humanity's most profound journey with billions of people who must imagine the perspective shift that comes from seeing Earth as a complete sphere hanging in cosmic darkness. The re-establishment of Earth contact also restores access to navigation updates from ground-based tracking stations that monitor the spacecraft's position with centimeter-level accuracy despite the 400,000-kilometer distance. The Deep Space Network, NASA's global array of radio telescopes, maintains continuous communication coverage through facilities in California, Spain, and Australia that compensate for Earth's rotation and ensure constant contact with spacecraft throughout the solar system. The same radio telescopes that communicate with interplanetary missions also conduct astronomical research, listening for signals from pulsars, quasars, and other cosmic phenomena that reveal the structure and evolution of the universe itself. Temperature control systems continue managing thermal loads as the spacecraft's orientation changes during its return trajectory, with different surfaces experiencing solar heating and cosmic cooling according to their exposure to direct sunlight and deep space. The crew module's environmental systems maintain comfortable temperatures through active thermal management that pumps heat from electronics and human metabolism to radiators that glow dull red as they dump waste energy into the 7 Kelvin background temperature that permeates intergalactic space. The crew begins preparing for the psychological transition from space travelers back to Earth inhabitants, though the profound perspective shift of seeing their home planet from lunar distance will influence their worldview permanently. Every astronaut who has experienced the overview effect reports lasting changes in how they understand national boundaries, environmental protection, and humanity's place in the cosmic order. The crew of Artemis II joins this select group of humans who have gained direct experiential knowledge that Earth represents a tiny oasis of life surrounded by hostile emptiness that extends billions of kilometers in all directions. Only took human consciousness 4 billion years to evolve sufficient complexity to contemplate its own cosmic context from outside the planet that created it. Navigation systems confirm that the spacecraft remains on its planned trajectory for Earth return, though small course corrections may be required to compensate for gravitational perturbations and ensure precision targeting of the recovery zone. The same mathematical techniques that guided Apollo missions safely home now navigate Artemis II through the gravitational environment of cislunar space, where Earth and Moon compete for influence over spacecraft motion according to laws of physics that have operated unchanged since the solar system formed 4.6 billion years ago. The Moon continues its ancient orbit around Earth, completing another revolution in its 3-day sidereal period while maintaining the same face toward Earth through tidal locking that synchronized lunar rotation and revolution billions of years ago. The spacecraft carries forward humanity's expanding presence in space, adding 4 more names to the list of people who have traveled beyond Earth's gravitational protection and experienced the profound isolation and beauty of interplanetary space. Radio signals continue flowing between spacecraft and Earth at light speed, carrying human voices and electronic data across the void that separates worlds, maintaining the electromagnetic connection that links 4 space travelers to the planet that will soon welcome them home from humanity's first lunar journey in over half a century. The spacecraft's trajectory evolves according to gravitational mathematics that transform its lunar flyby into preparation for humanity's next footsteps on another world, carrying aboard the accumulated data that will guide Artemis II when astronauts again touch ground that has waited 51 years for human visitors. Each measurement recorded during the 10-day mission radiation levels, navigation accuracy, thermal performance. Life support reliability contributes to the engineering knowledge needed to land crews safely on the lunar surface and return them to Earth with margins that reflect decades of technological advancement since the Apollo era ended in 1972. The crew's observations of potential landing sites provide direct human assessment of terrain that robotic reconnaissance missions have photographed and analyzed through automated systems. Their descriptions of crater morphologies, regolith characteristics, and local topography complement instrumental data with the pattern recognition capabilities that evolution refined across millions of years, but artificial intelligence has yet to replicate fully. Human observers possess intuitive understanding of terrain navigability, hazard assessment, and operational constraints that supplement the precise but limited perspectives provided by orbital cameras and spectrometers. Only took spaceflight technology 60 years to reach the point where human lunar surface operations become routine rather than experimental. The spacecraft carries data about cosmic radiation exposure that will inform medical protocols for future crews spending weeks rather than days beyond Earth's protective magnetosphere. Each crew member wears multiple dosimeters that record particle impacts from galactic cosmic rays, solar energetic particles, and trapped radiation within Earth's Van Allen belt's measurements that add to the database begun with the first Mercury flights and continued through every human mission beyond low Earth orbit. This accumulated radiation exposure data guides development of pharmaceutical countermeasures, habitat shielding requirements, and mission duration limits that balance scientific objectives against acceptable health risks. Artemis III mission planning proceeds on Earth while the crew continues their return journey, with engineers incorporating real-time performance data from Artemis II systems into designs for the human landing system that will carry 2 astronauts from lunar orbit to the surface and back. The same gravitational mechanics that govern the current crew's free return trajectory will guide future missions through more complex orbital choreography involving rendezvous, docking, and powered descent to the lunar surface using engines that must function flawlessly in the vacuum and thermal extremes that define the space environment. Scientists analyze preliminary results from instruments that measured the lunar environment during far-side passage, detecting trace gases, electromagnetic fields, and particle populations that reveal ongoing processes in the space surrounding the Moon. These measurements contribute to understanding how solar wind interacts with airless planetary bodies, how micrometeorite impacts release atoms and molecules from solid surfaces, and how electrical charging occurs on objects exposed to the plasma environment that permeates interplanetary space. The crew's successful navigation around the Moon demonstrates the maturity of guidance systems that began with mechanical gyroscopes and evolved into the digital navigation computers that now maintain trajectory accuracy measured in centimeters across interplanetary distances. The same inertial guidance principles that allowed submarines to navigate beneath polar ice during the Cold War now guide spacecraft through the electromagnetic interference and radiation environments that challenge electronic systems operating beyond Earth's protective atmosphere. Only took navigation technology 5 centuries to progress from celestial observation using astrolabes to automated spacecraft guidance using atomic clocks and laser ranging. Mission planners prepare for ocean recovery operations as the spacecraft approaches the point where Earth's gravity becomes dominant over lunar gravitational influence, marking the crew's transition from visitors to humanity's nearest celestial neighbor back to inhabitants of the world that shaped their species across 4 billion years of evolution. Pacific Ocean recovery ships position themselves within the predicted landing zone. Their crews trained in the precise procedures needed to safely retrieve 4 astronauts who have experienced 10 days of weightlessness and must readapt to Earth's gravitational field. The spacecraft's heat shield awaits its ultimate test during atmospheric entry at 11 kilometers per second, nearly 3 times faster than typical re-entry from low Earth orbit and fast enough to create plasma temperatures exceeding 2,700 degrees Celsius around the crew module. This thermal environment requires ablative materials that sacrifice themselves to protect the crew, burning away in controlled fashion while maintaining structural integrity sufficient to preserve the pressure vessel containing 4 human lives returning from the first lunar mission since the 20th century, ended. Life support systems continue maintaining Earth-normal atmospheric conditions within the crew module, recycling air and water with efficiency that demonstrates decades of refinement since early spacecraft required complete consumable replacement for missions lasting more than a few days. The environmental control and life support system aboard Artemis II represents evolutionary development of technologies that began with Project Mercury's simple oxygen supply systems and evolved through Gemini, Apollo, Space Shuttle, and International Space Station programs into the reliable life support architecture that enables extended human operations beyond Earth's atmosphere. The crew's physiological adaptation to weightlessness continues according to patterns documented by hundreds of previous astronauts, though individual responses vary based on genetics, fitness levels, and psychological factors that scientists still work to understand fully. Bone density decreases measurably during even brief space flights, muscle mass atrophies despite exercise countermeasures, and cardiovascular deconditioning occurs as blood redistribution eliminates the hydrostatic pressure gradients that normally challenge terrestrial circulation systems. Scientists still debate whether these physiological changes represent fundamental barriers to long-duration spaceflight or adaptation challenges that improved countermeasures and pharmaceutical interventions will eventually overcome. What remains certain is that human expansion beyond Earth requires medical solutions to biological problems that evolution never encountered during the 4 billion years when life remained confined to planetary surfaces, protected by atmospheric pressure and gravitational acceleration. Only took medicine 2 centuries to develop from bloodletting and mercury treatments into space medicine capable of maintaining human health in environments utterly hostile to biological survival. The spacecraft's successful systems performance provides confidence for Artemis III mission planning, demonstrating that life support, navigation, thermal control, and communication systems can operate reliably throughout the 10-day missions needed for lunar surface operations. Each system aboard the spacecraft incorporates redundancy and fault tolerance, learned from 60 years of human spaceflight experience, though the space environment continues to challenge engineering solutions with radiation effects, thermal cycling, and vacuum conditions that have no terrestrial equivalent. Ground-based mission controllers monitor thousands of telemetry parameters that report spacecraft health and crew status in real time, despite the 1-3-second communication delay that separates mission operations from the crew's actual experience. This remote monitoring capability represents the culmination of telemetry systems that began with simple radio beacons on early satellites and evolved into the comprehensive data streams that enable robotic missions throughout the solar system and human missions beyond low Earth orbit. The crew prepares mentally for their return to Earth's surface after experiencing the profound perspective shift that comes from seeing their home planet as a complete sphere suspended in cosmic darkness. This overview effect has influenced every human who has traveled beyond low Earth orbit, creating a psychological transformation that transcends national, cultural, and ideological boundaries. Through direct experiential knowledge of Earth's place in the cosmic order, navigation systems confirm that the spacecraft remains on its planned trajectory for Earth return, following the gravitational pathway that will deliver 4 space travelers safely back to the Pacific Ocean recovery zone, where ships wait to complete humanity's first lunar journey in over half a century. The same mathematics that guided their outbound trajectory now governs their return, demonstrating the reliability of celestial mechanics across the distances that separate worlds in the solar system, where human consciousness first arose and now begins to spread. The long journey home stretches across 4 days of interplanetary flight, as Earth's gravity gradually overcomes the Moon's diminishing influence and draws the spacecraft back toward the world that launched it 10 days earlier. Each hour of the return trajectory demonstrates gravitational mechanics operating at cosmic scale, where the same inverse square law that governs falling objects on Earth's surface now guides 4 human beings across 400,000 kilometers of vacuum toward their home planet. The spacecraft follows its predetermined path through space-time with mathematical precision, though small course corrections may be required to ensure accurate targeting of the Pacific Ocean recovery zone where naval vessels wait to complete the mission. Earth grows larger in the spacecraft windows according to geometry that makes distant objects appear to expand as observers approach them, though the visual effect remains subtle until the final day when the planet begins to display recognizable continental features rather than the abstract patches of brown and green that characterize the view from lunar distances. The same optical principles that allow telescopes to magnify distant celestial objects now work in reverse as the crew's proximity to Earth increases the planet's apparent angular size from a point of light to a marble to eventually a sphere that fills their entire field of view. Only took human vision 4 billion years of evolution to develop the neural processing capabilities needed to interpret perspective changes across interplanetary distances. The crew's daily routine maintains the artificial circadian rhythms that help human physiology function normally, despite the absence of natural day-night cycles that governed terrestrial life for billions of years before consciousness first contemplated the possibility of traveling between worlds. Artificial lighting within the crew module mimics Earth's 24-hour light patterns, while melatonin supplements and carefully timed meal schedules help regulate sleep-wake cycles that evolved under the influence of Earth's rotation, but must now operate independently of any external temporal references. Communication delays decrease gradually as the spacecraft approaches Earth, though radio signals still require over a second each direction when the crew reaches the planet's gravitational sphere of influence. These delays transform conversation into patient exchanges where questions and responses are separated by the fundamental limitations of electromagnetic propagation through vacuum, creating a communication protocol that bears little resemblance to terrestrial dialogue but becomes natural after days of practice. Mission control conversations take on ceremonial quality as each transmission carries human thoughts across distances that dwarf all Earthbound travel. The spacecraft's life support systems continue their reliable operation throughout the return journey, maintaining atmospheric pressure, temperature, humidity, and gas composition within the narrow ranges required for human survival, while recycling air and water with efficiency that represents decades of technological refinement. These environmental control systems create a tiny pocket of terrestrial conditions traveling through space at velocities that exceed the escape velocity of most asteroids, demonstrating humanity's growing capability to carry Earth-like environments beyond the planet's protective atmosphere. Scientific instruments throughout the spacecraft record continuous measurements of the cosmic radiation environment, magnetic field variations, and micrometeorite impacts that characterize interplanetary space between Earth and Moon. Each data point contributes to humanity's understanding of the space environment that future crews will encounter during missions to Mars, the asteroid belt, and eventually the outer planets where radiation levels increase dramatically and communication delays stretch to hours rather than seconds. Only took space science 6 decades to transform the region between Earth and Moon from complete mystery into a well-characterized environment suitable for routine human operations. The crew's physiological adaptation to weightlessness reaches equilibrium as their bodies complete the transition from terrestrial to space-adapted configuration, though this adaptation will reverse rapidly once Earth's gravity begins affecting their circulation, bone loading, and muscle function during atmospheric reentry and recovery operations. Medical monitoring continues throughout the return flight, as doctors on Earth track the crew's cardiovascular health, sleep patterns, and psychological well-being through telemetry data and voice communications that reveal how human biology responds to extended weightlessness. Bone density measurements will quantify mineral loss that occurs during even brief periods of weightlessness, while muscle strength tests will document the deconditioning that requires weeks of rehabilitation to reverse completely. These medical data contribute to understanding the physiological challenges that will affect crews during Mars missions lasting months or years, where weightlessness exposure far exceeds anything experienced during Apollo or Artemis lunar flights. Navigation systems maintain trajectory accuracy that allows mission planners to predict the spacecraft's Earth arrival time within minutes, despite the complex gravitational interactions that influence motion in the Earth-Moon system. Ground-based tracking stations monitor position and velocity continuously using radio ranging and Doppler shift measurements that provide navigation accuracy measured in meters across interplanetary distances. The same tracking techniques that guide robotic missions throughout the solar system now ensure that 4 human beings will arrive at precisely the correct location for safe ocean recovery. Temperature control becomes increasingly challenging as the spacecraft approaches Earth and solar heating intensifies due to the planet's closer proximity to the Sun relative to lunar distances. Thermal management systems work continuously to maintain comfortable crew compartment conditions while managing heat loads from electronics, human metabolism, and external solar radiation that varies with spacecraft orientation and orbital position. These thermal control requirements will become even more critical during future Mars missions, where spacecraft must operate in thermal environments that change dramatically throughout the 26-month synodic period between Earth and Mars. The crew begins psychological preparation for their return to Earth's surface and the readjustment to life in a gravitational environment after 10 days of weightlessness that have allowed them to experience motion in 3 dimensions without preferred directions. This transition from space travelers back to terrestrial inhabitants requires mental adaptation that complements the physical challenges of readjusting to weight, balance, and spatial orientation that define human experience on planetary surfaces. Only took human consciousness millions of years to develop the cognitive flexibility needed to adapt between terrestrial and space environments within days or weeks. Mission success becomes increasingly apparent as spacecraft systems continue operating nominally, and the crew maintains good health throughout their interplanetary journey. Each successful system demonstrates the maturity of space technology that began with experimental flights lasting minutes and has evolved into reliable transportation capable of carrying humans safely across the distances that separate worlds in the solar system. The spacecraft carries more than 4 human beings on their journey home. It transports the accumulated experience, scientific data, and technological validation that will enable Artemis II to achieve humanity's return to the lunar surface and establish the foundation for permanent human presence beyond Earth. This mission represents a bridge between the Apollo era's brief lunar visits and the sustained space exploration that will characterize the remainder of the 21st century. Radio communications with Earth carry increasingly excited voices as mission controllers, family members, and the global audience following the flight anticipate the crew's safe return from humanity's first lunar journey in over half a century. These electromagnetic signals travel at light speed across decreasing distances, carrying human emotions and technical data through the vacuum that separates worlds but cannot prevent the flow of information that connects space travelers to the planet that created their species. The spacecraft continues its gravitational fall toward Earth, following orbital mechanics that have governed celestial motion since the solar system formed from cosmic dust and gas. 6 billion years ago, carrying 4 space travelers home from the moon that has watched Earth's evolution throughout the entire history of complex life. The spacecraft accelerates toward Earth's atmosphere at 11 kilometers per second as gravitational potential energy converts to kinetic energy according to conservation laws that have governed celestial mechanics since the solar system condensed from the primordial disk of dust and gas that surrounded the infant sun. This velocity, nearly 3 times faster than typical reentries from low Earth orbit, will create plasma temperatures exceeding 2,700 degrees Celsius around the crew module, as atmospheric friction converts the spacecraft's enormous kinetic energy into heat that must be absorbed by ablative materials designed to sacrifice themselves while protecting 4 human lives returning from lunar distance. The heat shield that will soon face Earth's atmosphere measures 5 meters across and weighs 1,600 kilograms. Its honeycomb structure filled with Avcoat ablative material that represents the culmination of thermal protection technology developed since the first spacecraft began returning from orbital velocities in the 1960s. Each hexagonal tile contains phenolic resin that will char, burn, and blow away in controlled fashion during atmospheric entry, carrying away heat through mass loss rather than conduction, a process that transforms solid spacecraft components into plasma and gas that streams away at temperatures hot enough to dissociate molecular bonds and ionize atmospheric atoms. Only took materials science 6 decades to develop substances capable of surviving the thermal violence that occurs when interplanetary velocities meet atmospheric resistance. The crew prepares for atmospheric entry by securing loose equipment, checking restraint systems, and configuring spacecraft controls for the automated sequence that will guide them through the most dangerous phase of their 10-day journey. Human reflexes cannot respond quickly enough to control spacecraft attitude during hypersonic flight through Earth's upper atmosphere, where aerodynamic forces change faster than conscious thought and require computer-controlled reaction control systems operating at millisecond timescales to maintain the precise orientation needed for survival. Earth's atmosphere extends far higher than most people realize, with measurable atmospheric drag affecting spacecraft at altitudes exceeding 200 kilometers, where atmospheric density remains 1/1000th of sea level values. The spacecraft will encounter this tenuous upper atmosphere at entry interface 100 kilometers altitude by international convention, beginning the transition from ballistic flight through vacuum to aerodynamic flight through increasingly dense atmospheric layers that will decelerate 4 human beings from interplanetary to parachute deployment velocities in less than 15 minutes. The entry trajectory follows a precise corridor that balances heating rates against deceleration forces, approaching Earth's atmosphere at an angle shallow enough to prevent excessive thermal loads, while steep enough to avoid skipping back into space like a stone across water. This entry corridor measures only a few degrees wide, miss it by flying too steeply, and the crew experiences deceleration forces that can cause unconsciousness or death. Approach too shallow and insufficient atmospheric braking may prevent successful parachute deployment and ocean landing. Scientists have calculated that atmospheric entry from lunar return velocities subjects the crew to peak deceleration forces approaching 8 times Earth's gravitational acceleration, enough to make their arms feel like concrete pillars and their heads weigh as much as bowling balls. These forces last only minutes, but require physical conditioning and restraint systems designed to prevent injury during the most violent deceleration that healthy humans can survive without permanent physiological damage. Only took aerospace medicine half a century to understand the limits of human tolerance to the acceleration forces that define high-performance flight and spacecraft operations. The heat shield's thermal protection system operates through ablation, a process where surface materials absorb heat by changing phase from solid to liquid to gas, and finally to plasma that carries energy away from the spacecraft structure. This ablative cooling represents one of nature's most efficient heat transfer mechanisms, used by everything from meteor showers that create shooting stars to the thermal protection systems that enable interplanetary spacecraft to survive atmospheric entry at velocities that would vaporize unprotected vehicles instantly. Plasma formation around the spacecraft creates a communications blackout that severs radio contact with Earth for approximately 4 minutes, as ionized atmospheric gases reflect and absorb electromagnetic radiation across the frequency spectrum used for spacecraft communication. This blackout represents the crew's final isolation from Earth, though they remain only minutes away from parachute deployment and the recovery ships that wait in the Pacific Ocean to complete their journey home from humanity's first lunar mission in over 50 years. The entry plasma glows with the characteristic colors of atmospheric gases heated to temperatures that approach those found in stellar photospheres, creating a man-made aurora around the spacecraft as oxygen atoms emit green light and nitrogen molecules produce red and blue emissions. Ground-based observers may see this artificial meteor streak across the pre-dawn sky, a brief star created by human technology returning from the cosmos at velocities that transform atmospheric molecules into light. Navigation during entry relies entirely on inertial guidance systems that maintain attitude and velocity information despite the loss of ground-based tracking data during plasma blackout. The spacecraft's computers execute pre-programmed control sequences that adjust vehicle orientation to maintain the precise flight path needed for accurate landing, while atmospheric turbulence and ablative mass loss continuously alter aerodynamic characteristics in ways that require constant compensation through reaction control system burns. Only took guidance technology 4 decades to evolve from mechanical gyroscopes to digital systems capable of autonomous navigation through atmospheric entry at interplanetary velocities. The crew experiences the return of weight as deceleration forces gradually overcome the weightlessness they have experienced for 10 days. Their cardiovascular systems suddenly required to pump blood against gravitational acceleration that their bodies have temporarily forgotten how to anticipate. Inner ear balance organs readjust to vertical orientation cues, while proprioceptive systems relearn the relationship between muscle tension and limb position in Earth's gravitational field. Peak heating occurs at approximately 70 kilometers altitude, where atmospheric density reaches optimal values for maximum energy transfer from the spacecraft's kinetic energy to thermal energy that must be absorbed and dissipated by the heat shield. Surface temperatures exceed the melting points of most metals as the Avcoat ablative material performs its designed function, charring and burning away while maintaining sufficient structural integrity to protect the crew compartment from thermal penetration. The spacecraft's communication systems automatically attempt to re-establish contact with recovery forces as the plasma sheath begins dissipating and electromagnetic transparency returns to the atmosphere surrounding the vehicle. Radio signals once again span the gap between spacecraft and Earth, though now measured in tens of kilometers rather than hundreds of thousands, as the crew approaches the Pacific Ocean, where their 10-day journey began with launch from Florida's Atlantic coast. Parachute deployment sequences begin as atmospheric density increases, and spacecraft velocity decreases to the point where fabric parachutes can deploy without being destroyed by aerodynamic forces that earlier in the entry would have torn any material to pieces instantly. 3 main parachutes, each larger than a basketball court, will slow the crew's descent from hundreds of kilometers per hour to approximately 30 kilometers per hour for ocean impact that spacecraft structure can survive while protecting the crew from deceleration forces that could cause injury. The heat shield completes its mission as atmospheric heating ends and the spacecraft transitions from hypersonic entry vehicle to subsonic parachute payload, descending toward ocean recovery. Tons of ablative material have burned away during the 15-minute entry sequence, transformed from solid spacecraft components into plasma and gas that now disperses through Earth's upper atmosphere as testimony to the thermal violence that occurs when human ambition meets the fundamental physics governing motion between worlds. Recovery ships track the spacecraft's descent using radar systems that provide position updates to guide helicopters and boats toward the floating crew module that will complete humanity's return to lunar exploration after a hiatus that lasted longer than most space program participants initially expected when Apollo 17 departed the Moon in December 1972. The three main parachutes bloom above the spacecraft like fabric flowers opening against the Pacific dawn sky. Their orange and white canopies, larger than basketball courts and strong enough to support 9,000 kilograms of crew module and heat shield, descending toward ocean waters that have waited 4.5 billion years to receive visitors returning from another world. Each parachute represents the culmination of textile engineering refined through decades of spacecraft recovery operations, woven from materials that must deploy reliably at high altitudes where atmospheric density barely supports aerodynamic loading, then function flawlessly during the crucial minutes that separate successful ocean landing from catastrophic impact. The crew experiences the gentle deceleration of parachute descent after the violence of atmospheric entry, their bodies readjusting to weight and vertical orientation as Earth's gravitational field reasserts its influence over human physiology that spent 10 days adapting to the weightless environment of interplanetary space. Inner ear balance organs recalibrate to process acceleration cues in 3 dimensions rather than the arbitrary orientations that characterize their lunar journey, while cardiovascular systems pump blood against hydrostatic pressure gradients that disappeared during launch and now return with the inevitability of physics governing fluid behavior in gravitational fields. Only took parachute technology 5 centuries to evolve from Leonardo da Vinci's sketches into life support systems capable of delivering astronauts safely home from lunar distances. The Pacific Ocean stretches to all horizons below the descending spacecraft, its surface marked by swells generated by storm systems thousands of kilometers away, and wind patterns driven by pressure gradients that have circulated through Earth's atmosphere since water first condensed from volcanic outgassing 3.5 billion years ago. This same ocean covers most of the planet that appears as a blue marble from lunar distance, demonstrating the abundance of liquid water that makes Earth unique among known worlds and enables the biological processes that created the consciousness now returning from its first extended journey beyond terrestrial protection. Recovery ships converge on the predicted landing zone using GPS navigation systems that require relativistic corrections to maintain accuracy, compensating for the time dilation effects that atomic clocks experience in Earth's gravitational field and the orbital velocities of positioning satellites. The same physics that Einstein described in his theories of special and general relativity now guides recovery operations for astronauts, whose high-velocity journey has subjected them to measurable time dilation effects, nanoseconds of temporal difference that demonstrate the relationship between gravity, acceleration, and the passage of time itself. Radio communications crackle with reports from helicopter crews, naval vessels, and mission controllers as the spacecraft approaches ocean impact at approximately 30 kilometers per hour, fast enough to require careful crew preparation, but slow enough to allow survival in a vehicle designed to protect human occupants during controlled crashes into water that provides more forgiving impact characteristics than solid ground. The crew module structure incorporates energy-absorbing materials and crush zones that manage impact forces while maintaining crew compartment integrity throughout the deceleration sequence that marks their transition from space travelers to ocean survivors. The heat shield has completed its mission during atmospheric entry. Tons of AVCOAT ablative material transformed into plasma and gas that now disperses through the upper atmosphere as molecular testimony to the thermal violence required when interplanetary velocities encounter atmospheric resistance. What remains of the heat shield will separate from the crew module just before ocean impact, allowing the spacecraft to assume its designed floating orientation with hatches accessible to recovery divers who will secure the vehicle and assist the crew during their first moments back in Earth's gravitational field. Scientists still debate whether ocean recovery represents the optimal approach for future lunar missions, or whether runway landings might provide gentler crew experiences and better spacecraft reusability. What remains certain is that ocean recovery has successfully returned every Apollo crew from lunar missions and provides operational flexibility that accommodates trajectory dispersions and weather variations that could complicate precision landing attempts at terrestrial airports. Only took spacecraft recovery technology 6 decades to transform ocean splashdown from experimental necessity into routine operational procedure. The crew prepares for ocean impact by assuming positions that distribute deceleration forces evenly across their bodies, while restraint systems prevent injury during the controlled crash that ends every ballistic spacecraft mission. Their 10-day journey from Earth to Moon and back concludes with a few seconds of deceleration that transforms their motion from controlled flight to floating survival as the spacecraft becomes a life raft designed to maintain crew safety until recovery forces can complete rescue operations. Ocean impact occurs with precisely the velocity that parachute deployment calculations predicted, demonstrating the reliability of aerodynamic systems that must function perfectly despite operating in atmospheric conditions that change constantly due to weather patterns, seasonal variations, and the complex fluid dynamics that govern air movement around parachute canopies falling through density gradients. The spacecraft's crew compartment remains intact and watertight as designed, protecting 4 astronauts who have traveled farther from Earth than any humans since 1972. The crew module assumes its stable floating attitude as recovery swimmers approach the spacecraft to begin post-landing procedures that will extract the astronauts and transport them to the recovery ship, where medical teams wait to begin the physiological assessments that will document how human biology responds to 10 days of weightlessness, followed by the deceleration forces of atmospheric entry and ocean impact. These medical evaluations contribute to the database that guides crew selection and training for future lunar missions, and eventually Mars expeditions where physiological challenges will increase dramatically due to mission durations measured in years rather than days. Recovery operations proceed according to procedures refined through decades of spacecraft retrieval experience, with specialized equipment designed to handle crew modules that may be contaminated with toxic propellants, damaged by entry heating, or structurally compromised by impact forces. Professional rescue swimmers secure the spacecraft, while helicopters and boats establish communication with the crew and prepare for the careful extraction procedures needed to assist astronauts who have spent 10 days in weightlessness and may require medical support during their readaptation to Earth's gravitational environment. Only took recovery technology 50 years to evolve from experimental Apollo procedures into routine operations capable of retrieving crews from any ocean landing zone within Earth's latitude range. The 4 crew members emerge from their spacecraft as returning heroes who have accomplished humanity's first lunar journey in over half a century, carrying with them the scientific data, operational experience, and psychological transformation that will enable Artemis II to achieve the next milestone in space exploration, humanity's return to the lunar surface for the first sustained exploration of another world. Their safe recovery represents the successful completion of the most ambitious space mission since the Apollo era ended and demonstrates humanity's restored capability to travel beyond Earth's protective atmosphere. The spacecraft floats on Pacific swells as recovery teams work to secure the vehicle and extract crew members who have experienced the profound perspective shift that comes from seeing Earth as a distant blue star surrounded by cosmic emptiness. The same ocean that covers most of their home planet now welcomes them back from the Moon that continues its ancient orbit, patient and unchanging, waiting for the next human visitors who will soon follow the path that Artemis II has reopened. Medical teams begin preliminary health assessments while the crew adapts to breathing unprocessed atmospheric air, feeling ocean spray on their faces, and experiencing the weight of their own bodies after 10 days of weightlessness that temporarily transformed them from terrestrial creatures into space-adapted beings. Their journey ends where it began on the surface of the water world that gave birth to consciousness, and now watches that consciousness return from its first extended exploration of the cosmos beyond terrestrial boundaries. The recovery ship approaches through swells generated by gravitational forces that have connected Earth and Moon for 4.5 billion years, completing the circle that began with launch from Florida's coast and concludes with retrieval from Pacific waters. 4 space travelers have safely returned from humanity's nearest celestial neighbor, bringing home the knowledge and experience needed to guide the species toward permanent residence among the worlds that orbit the Sun. The spacecraft rests quietly on Pacific swells as recovery operations near completion, its heat shield scarred by entry plasma and its parachutes trailing in ocean currents that have circulated through Earth's waters since tidal forces first began stirring primordial seas 3.5 billion years ago. 4 astronauts sit safely within their crew module, breathing salt air that connects them once again to the planet they briefly left behind. Their 10-day journey complete, except for the gentle transition from ocean survivors back to terrestrial inhabitants of the world that shaped their species across countless generations. Above them, the Moon continues its ancient progress across Earth's sky, invisible in daylight but present nonetheless, maintaining its gravitational influence over ocean tides that lift recovery ships and spacecraft with the same rhythmic pulse that has marked time since continents first began drifting across the planet's surface. The lunar companion that guided their journey now resumes its patient vigil, waiting for the next human visitors who will follow the path that Artemis II has reopened after 51 years of absence. The crew's voices carry across radio frequencies as they report their condition to medical teams, their words traveling at light speed through Earth's atmosphere with the same electromagnetic radiation that maintained their connection to home throughout their interplanetary journey. These final transmissions from space mark the end of humanity's first lunar mission since the 20th century, concluded, completing a chapter in space exploration that began with dreams of cosmic travel and concludes with the practical reality of routine transportation between worlds. Recovery ships approach through morning light that illuminates ocean surfaces with the same solar radiation that heated their spacecraft during transit between Earth and Moon, demonstrating the universality of physical processes that govern energy transfer across all distances in the solar system. The Sun continues its ancient fusion reactions 38 million kilometers away, converting hydrogen to helium at rates that have sustained all terrestrial life throughout the 4 billion years since photosynthesis first began transforming starlight into biological energy. Only the gentle motion of ocean swells disturbs the profound stillness that settles over the recovery zone as human consciousness returns from its brief exploration of cosmic distances. The spacecraft floats in perfect stability, its mission accomplished, its crew safe, its journey complete. Pacific waters accept this visitor from space with the same indifference that oceans have shown to every returning meteorite. Spacecraft, an asteroid that has completed the ancient cycle of departure and return that governs all motion between the worlds. The 4 astronauts rest quietly in their seats, processing memories of Earth seen from lunar distance, of radio silence behind the Moon's bulk, of cosmic radiation measured in particle impacts per second rather than terrestrial time. Their experiences join the accumulated wisdom of space exploration, adding 4 more voices to the small community of humans who have traveled beyond Earth's gravitational protection and witness the profound beauty and isolation of interplanetary space. Gentle waves rock the spacecraft as recovery operations continue with methodical precision. Each procedure refined through decades of practice until ocean retrieval becomes as routine as any terrestrial rescue operation. The crew waits patiently for extraction, their bodies readjusting to weight and balance, while their minds begin the longer process of integrating the perspective shift that comes from seeing their entire world as a distant point of light suspended in cosmic darkness. The moon sets below the horizon, invisible but eternal, carrying forward the gravitational influence that will continue shaping Earth's tides, climate, and rotational stability for billions of years after human consciousness expands throughout the solar system and beyond. The ancient dance between Earth and Moon continues unchanged, marked now by the successful return of 4 space travelers who have added their names to the brief list of humans who have journeyed to another world and returned safely home. Silence settles across the recovery zone as operations near completion, broken only by the whisper of wind across ocean swells and the distant sound of helicopter rotors carrying medical teams toward the floating spacecraft. The crew rests in perfect stillness, their great journey complete, their safe return accomplished, their contribution to human space exploration secured for all the generations that will follow their pioneering path to the moon and beyond. The Pacific Ocean accepts their return with ancient patience, its waters unchanged by their presence, its tides continuing their eternal rhythm as Earth and Moon maintain the gravitational partnership that has endured since the solar system's violent birth 4.5 billion years ago.